This is literally everything there is to know about chemistry, the history, how it works, and some theories, predictions for the future, and much, much more. Before we begin, make sure you are subscribed, and if you want to listen to these videos on Spotify without ads, or just support the channel, join my Patreon with the first link in the description, and let's begin. So let's start at the very beginning. Not the beginning of the universe, we'll get there, but the beginning of human chemistry, which happened before anyone called it chemistry, before there were scientists, before there was even writing. The first time a human being did chemistry, they were almost certainly doing it by accident, standing a little too close to a fire and watching something unexpected happen. Fire was the first chemical reaction that humans ever controlled, and its importance to the development of civilization is almost impossible to overstate. The thing about fire is that it doesn't just consume, it transforms. Wood goes in, smoke and heat, and ash come out, and the mass of everything doesn't add up the way you'd naively expect. Early humans didn't know why. They just knew that fire changed things in ways that nothing else did. And the people who paid attention to what it changed, under what conditions, with what starting materials, were the first chemists on Earth, even if they would never have used that word. The oldest confirmed chemical technology humans developed was probably the controlled use of pigments. About 30,000 years ago, maybe earlier, people were grinding and heating ochre, a reddish mineral containing iron compounds, to produce pigments for cave paintings. The key word there is heating. Heating ochre changes its color properties in a controlled way, from yellow to red to darker shades. Someone discovered this, repeated it, taught it to someone else. That's chemistry as a technology. Deliberate manipulation of matter to change its properties. Then came metallurgy, and this is where chemistry started to reshape the entire trajectory of human civilization. Copper was probably the first metal humans worked with deliberately around 9,000 years ago. At first, people found copper in its native form, just sitting in rocks looking metallic, and hammered it into tools. But native copper isn't very common. Somewhere along the line, someone discovered that certain greenish rocks, when placed in a hot enough fire, produced liquid metal. That's melting. Copper ore, like malachite or azurite, contains copper locked in chemical compounds with oxygen and carbonate. When you heat it with charcoal, the carbon reacts with the oxygen, pulling it away from the copper, and you're left with pure metal pooling at the bottom of your fire. The heat drove a chemical reaction. The chemical reaction gave you copper. This was a profound discovery because it meant you could get metal from rocks that looked nothing like metal. The metal was hiding inside, bound to other elements in invisible chemical relationships, and the right amount of heat was the key that broke those relationships and set it free. Bronze came about 5,000 years ago, and bronze is chemically interesting because it's not a single element. It's an alloy, a mixture of copper and tin, and it's significantly harder than either metal on its own. Somebody, somewhere, mixing two metals got something better than both. That's a chemical insight. Combining things sometimes produces something qualitatively different from its components. The search for better alloys drove metallurgical chemistry for centuries. Iron came next, harder to extract because it requires higher furnace temperatures and differently behaved. Unlike copper, iron, at the temperatures early furnaces could reach, doesn't pour as a liquid, but has to be hammered and worked while hot. But iron ore is vastly more common than copper or tin, which means iron transformed who had access to metal tools and weapons. The Iron Age wasn't just a technological shift in what things were made of. It was a chemical shift in the economics of power. All of this, the pigments, the metals, the glazes on pottery, the soap made from animal fat and wood ash, the fermented beer in clay jars, all of this was chemistry being done in the complete absence of any theoretical framework. Nobody could explain why the malachite rock produced copper. Nobody knew what an atom was. The knowledge was entirely empirical. Do this under these conditions, and this is what you get. A practical recipe book with no explanation for why any of the recipes worked. Building the explanation was going to take a very long time. The first serious attempt to explain what matter was made of came from ancient Greece, and the way the Greeks went about it was characteristic of their intellectual culture. They thought about it, they argued, they wrote long philosophical texts speculating about the nature of things without any systematic experimentation to test their ideas. This produced some results that were remarkably prescient and some that dominated Western thought for nearly 2,000 years and turned out to be completely wrong. The prescient ones came from Leucippus and his student Democritus, working around 460 years before the Common Era. Their idea was that all matter was made of tiny, indivisible, indestructible particles, atoms, from the Greek for uncuttable. These particles moved through empty void. Different types of matter had different atoms, and the properties of a substance, its texture, its weight, its behavior, came from the shapes and arrangements of its atoms. You couldn't cut an atom in half. You couldn't create new atoms or destroy existing ones. The total amount of matter in the universe was fixed. This is a genuinely extraordinary idea to arrive at purely through reasoning, with no instruments, no experiments, no data beyond casual observation of the visible world. The specific details were wrong. Democritus thought atoms had little hooks that let them grab onto each other, which is not how it works, but the core framework was right. Matter is made of small, discrete, invisible particles. The properties of substances emerge from how those particles are arranged and how they interact. The problem was Aristotle. Aristotle was the most comprehensively influential philosopher in the ancient world, and he rejected atomism. In its place, he proposed that all matter was made of four elements: earth, water, fire and air, combined with two pairs of qualities, hot and cold, wet and dry. Earth was cold and dry, water was cold and wet, air was hot and wet, fire was hot and dry. Every substance in the world was some mixture of these four elements with these qualities. Change the proportions, and you changed the substance. This isn't completely crazy as a framework. It captures something real. Different substances do differ in temperature, humidity, and combustibility, but it's wrong in all the specifics that matter. Fire isn't an element. Water isn't an element. And the whole framework of qualities was too vague to make precise predictions, too flexible to be falsified by any experiment. Because Aristotle was so revered, his ideas were so comprehensive, so systematically argued, and so bundled into the educational institutions of both the Islamic world and medieval Europe. The four-element theory dominated Western thinking about matter for nearly 2,000 years. 2,000 years in which the correct explanation of matter, the atomic one, which Democritus had already articulated, sat largely ignored. The practical consequence was that the people doing the most sophisticated chemistry in the world during those 2,000 years were working within a framework that gave them a certain kind of goal. If all matter is the same stuff in different proportions, you should be able to rearrange those proportions and turn any substance into any other substance without giving them the right tools to achieve it or explain why it wasn't working. Alchemy tends to get treated condescendingly today. People know it as the failed predecessor to chemistry, the thing where deluded mystics tried to turn lead into gold and failed. That framing misses almost everything important. Alchemy was a serious intellectual pursuit practiced by some of the most educated, curious, and practically skilled people of their time across multiple cultures simultaneously. In China, in the Islamic world, in medieval Europe, people who called themselves alchemists were doing real chemical work, distilling substances, observing reactions, developing techniques, recording results. The difference between alchemy and chemistry isn't the quality of the curiosity or even the rigor of the observation. It's the theoretical framework that was available to make sense of what they were seeing. In the Islamic world, the alchemist Jabir ibn Hayyan, known in the West as Geber, was writing detailed practical guides to chemical procedures in the 8th and 9th centuries. His work on acids, salts, and the preparation of various chemical compounds was detailed enough to remain useful for 1,000 years. He described how to make sulfuric acid, nitric acid, and hydrochloric acid. He worked out procedures for crystallization, sublimation, and distillation. He documented observations about how metals dissolved in acids and how solutions behaved when heated. This is chemistry, even if the theoretical scaffolding around it included ideas we'd now call mystical. The alchemists invented most of the basic techniques and equipment of laboratory chemistry: the reflux condenser, the water bath, the alembic for distillation, the crucible for high temperature work, filtration, precipitation, recrystallization. These techniques were developed and refined over centuries by people working to understand matter, even if their understanding of what they were looking for was wrong. The practice was real even when the theory was off. The great alchemical dream, the philosopher's stone that could turn base metals into gold and also extend life indefinitely, attracted not just credulous dreamers but genuinely brilliant people. Roger Bacon, the 13th century friar who argued for empirical observation centuries before it became standard, was deeply engaged with alchemy. Robert Boyle, who is often called the father of modern chemistry, was interested in alchemy and corresponded with alchemists. Isaac Newton spent more time on alchemy than on the physics and mathematics we remember him for. His alchemical notebooks run to hundreds of thousands of words and show a deeply engaged, serious researcher trying to work within an inadequate framework. These weren't fools. They were among the most capable minds of their time. They were working on the best available theoretical framework, which happened to be wrong about some crucial things. The Chinese alchemical tradition focused more on the elixir of immortality than on transmutation, and the results were often grimly ironic. Multiple Chinese emperors who sought immortality through alchemical elixirs died young, almost certainly from mercury or lead poisoning in the very potions they were drinking to extend their lives. The desire to escape death, pursued with materials whose toxicity wasn't understood, killed the people who most wanted to survive. In medieval Europe, alchemy took on an additional layer of symbolic and spiritual meaning. The transmutation of lead into gold became a metaphor for spiritual transformation, the impure soul becoming pure. This mystical overlay sometimes obscured the practical chemical work, but it also provided cover for doing it. Alchemy was pursued by monks and scholars who might not have been permitted to do mere craftwork. The symbolic tradition and the practical tradition coexisted, feeding each other and sometimes getting tangled together. The failure that ultimately broke alchemy was a specific one. It wasn't just that nobody ever made gold from lead. It was that the more carefully people measured their materials and products, the more the four-element framework failed to make sense of what they were seeing. Weights didn't add up the way the theory predicted. Substances that should transform into each other refused to. The data and the framework were increasingly in tension, and the 17th century produced the first generation of thinkers willing to explicitly say so. The person who said it most clearly was Robert Boyle. Boyle was born in Ireland in 1627 into a wealthy aristocratic family, and he spent much of his adult life in Oxford and London doing precisely the kind of careful, quantitative, repeatable experiments that alchemy, at its best, aspired to, but rarely managed consistently. He designed experiments, wrote up results, published them so others could verify. He collaborated with other investigators. He was skeptical of authority, including Aristotle's, in a way that was genuinely unusual for his time. His book, The Skeptical Chemist, published in 1661, is one of the founding documents of modern chemistry. In it, Boyle methodically dismantled the four-element theory and the three-principle theory of the Paracelsian alchemists, who had replaced earth, water, fire, and air with salt, sulfur, and mercury, and argued that neither framework was adequate to explain what was actually observed in experiments. He didn't have a complete replacement. He was mostly doing criticism, but the criticism was devastating, and it cleared the way. Boyle's own positive contribution was quantitative work on gases. He showed, through careful experiments with an air pump he built with Robert Hooke, that when you compress a gas, its pressure increases in exact proportion to the decrease in volume. Double the pressure, halve the volume, triple the pressure, 1/3 the volume. The relationship was mathematically exact and reproducible. This was Boyle's law, and it was the first mathematically rigorous, experimentally derived relationship between measurable properties of a chemical substance. The significance isn't just the law itself, it's the method. Boyle wasn't reasoning from philosophical principles about the nature of air. He was measuring, he was generating data and finding patterns in it. He was doing science in the way we now recognize as science, and the patterns he found were precise and mathematical in a way that felt entirely different from the vague qualitative statements of the Aristotelian tradition. The adoption of the balance, the weighing scale, by chemists in the 17th and 18th centuries was similarly transformative. Once you started weighing everything before and after a chemical process, you started noticing things that demanded explanation. When a candle burned, it got lighter. When a metal sat in moist air, it got heavier. When you dissolved metal in acid, the acid became heavier and the metal vanished. Mass was going somewhere or coming from somewhere, and nobody could account for it properly. This was the central problem that the 18th century's greatest chemist was born to solve. Antoine Laurent de Lavoisier was born in Paris in 1743 into a wealthy family, and by his 30s, he had built one of the finest chemical laboratories in the world in his own home. He had money, intelligence, extraordinary experimental precision, and a remarkable collaborator in his wife, Marianne, who was herself a serious scientific contributor. She translated English and Latin chemistry papers for him, crucially important, since she could read English and he largely couldn't, drew detailed technical engravings of their laboratory apparatus, and participated directly in designing and running experiments. She essentially co-authored much of his published work, though the conventions of the time meant her name appeared on none of it. When Lavoisier started doing serious chemistry, the dominant theory of combustion was the phlogiston theory, and it was genuinely clever as theories go. Phlogiston was supposed to be a substance contained in anything flammable. When something burned, it released its phlogiston into the surrounding air. When the air became saturated with phlogiston and could absorb no more, combustion stopped, which explained why a candle under a sealed jar eventually went out. When metals rusted, they were also releasing phlogiston, just more slowly. When you heated a metal powder in the presence of charcoal, the charcoal, rich in phlogiston, transferred its phlogiston to the metal powder and restored the metal. The theory explained a lot of observations in a coherent, internally consistent way. The problem Lavoisier kept running into was mass. When a metal rusted, it got heavier. If it was releasing phlogiston, it should get lighter. The weight went up when it should have gone down. Some proponents of phlogiston argued that phlogiston had negative weight, that it actively made things lighter, so releasing it made things heavier. This isn't completely unreasonable as a theoretical patch, but it's the kind of patch that makes a theory increasingly baroque and unconvincing. Lavoisier's approach was to make the weighing more rigorous and more systematic than anyone had done before. He used closed vessels so no gas could escape unaccounted for. He weighed everything that went in and everything that came out. He treated mass balance as an absolute requirement. Every milligram had to be accounted for. And what he found over and over was that when things burned or rusted, they gained mass from the air, not lost it. Something in the air was combining with the burning substance. The air wasn't receiving something from the fire, it was giving something to it. The crucial piece arrived in 1774 when Joseph Priestley visited Paris. Priestley was a brilliant English nonconformist minister who did chemistry as a sideline and whose experimental skill was extraordinary. He'd heated a bright red mercury compound, what we'd call mercury oxide, and collected the gas released. Mice in a sealed jar with this gas lived longer than mice in ordinary air. Candles burned more brightly. He was convinced he'd isolated air from which all the phlogiston had been removed. Dephlogisticated air, he called it, because air stripped of phlogiston should be better at absorbing more phlogiston, which is what it appeared to do. Priestley described his experiments to Lavoisier over dinner in Paris. Lavoisier immediately grasped the significance of the gas. He replicated the experiments, extended them, and came to a completely different interpretation. The gas wasn't air stripped of phlogiston. It was a substance that things combined with when they burned. He ran the entire experiment backwards, starting with the gas, combining it with metals, carefully weighing everything, and showed that the mass gained by the metal was exactly equal to the mass of gas absorbed. There was no phlogiston. There was no mysterious substance being released. There was this gas, which Lavoisier named oxygen, combining with substances during combustion and rusting, and the combined product weighed more than the original substance by exactly the weight of the oxygen consumed. Mass was conserved, nothing created, nothing destroyed, just rearranged. The law of conservation of mass, which Lavoisier articulated clearly and demonstrated quantitatively, was a foundational moment in the history of science. It's so embedded in how we think about chemistry today that it seems obvious, but it wasn't obvious. It was a discovery, and it required years of careful, systematic weighing and a willingness to follow the data wherever it led, even when it contradicted the most successful theory in the field. Lavoisier's revolution didn't stop at oxygen. He completely rewrote the naming system of chemistry so that chemical names reflected composition rather than tradition, copper sulfate rather than blue vitriol, for example. He defined what a chemical element actually was, operationally, a substance that couldn't be broken down further by any known chemical means. He published a list of 33 elements, including some that we now know weren't elements. He listed light and heat as elements, and later work showed that some of his others weren't elementary, but the framework was right and most of the list was correct. He wrote the first modern chemistry textbook, Traité élémentaire de chimie, published in 1789. It laid out the law of conservation of mass, the theory of oxygen and combustion, and a systematic approach to chemical composition and naming. It was a complete break from the past. Chemistry, as we mean it now, starts with that book. Then, in 1794, during the Reign of Terror, Lavoisier was arrested and guillotined by the French revolutionary government. The specific charge was connected to his former role as a tax collector for the Ancien Régime, not his chemistry. The mathematician Joseph Louis Lagrange remarked afterward that it took only a moment to cut off his head, but 100 years might not produce another like it. He was 50 years old. The next major gap that chemistry needed to close was this. Lavoisier had established that elements existed and that chemical reactions rearranged them. But why did elements always combine in fixed whole number ratios? If you made water from hydrogen and oxygen, you always needed exactly 2 volumes of hydrogen per 1 volume of oxygen, not 1.5, not 2 1/3, always exactly 2 to 1. Why whole numbers? John Dalton, an English chemist and meteorologist working in Manchester at the start of the 19th century, answered the question with his atomic theory, published in 1808. His answer was simple. Because atoms are discrete, indivisible particles, and chemical reactions involve whole atoms combining with whole atoms, you can't have half an atom. So the ratios will always be small whole numbers. the observed law of definite proportions and the law of multiple proportions, he also explained, followed directly from the assumption that reactions involved atoms combining in specific ratios. Dalton's atoms were tiny, solid spheres. Different elements had different masses. He could establish the relative masses of atoms by measuring how much of each element went into compounds, even though he couldn't see the atoms themselves. He was reconstructing properties of invisible particles from patterns in visible measurements. The hydrogen atom being the lightest, he assigned a mass of 1. Oxygen atoms turned out to be 16 times heavier. Carbon 12 times heavier than hydrogen. These numbers, derived from careful mass measurements of chemical reactions, turned out to be almost exactly right. What Dalton couldn't explain was why different elements had different masses. The atoms were just different, with different properties, and that was that. The why was going to require much deeper physics. While chemists grappled with atomic masses and tried to figure out exactly how heavy each atom was relative to the others, a surprisingly thorny problem that led to decades of confusion and disputes. The list of known elements kept growing. New elements were being found by heating minerals, collecting unknown gases, doing careful analysis to show that what seemed like a single substance was actually several. By the mid-1800s, more than 60 elements were known, and the sheer number was becoming unwieldy. Chemists needed a way to organize them. Multiple people were working on this problem simultaneously. The English chemist John Newlands noticed in the 1860s that if you arranged elements in order of atomic weight, similar properties showed up every 8 elements, what he called the law of octaves. By analogy with musical octaves, his colleagues in the Chemical Society of London laughed at him and asked if he tried arranging the elements alphabetically. He hadn't invented the periodic table, but he had seen the periodicity. Dmitri Mendeleev arrived at the complete solution in 1869, and the story of how he got there is worth telling. He was a chemistry professor in St. Petersburg, working on a textbook. He needed a way to organize the elements for his students. He wrote all 60-odd known elements on separate cards, including their properties and atomic weights, and arranged and rearranged them, looking for a pattern. What he found was that when you arrange elements in order of increasing atomic weight and break them into rows such that similar elements line up in the same column, the pattern holds up remarkably well, with some exceptions where you have to put an element slightly out of order to keep the properties aligned in columns. What made Mendeleev's table more than just an organizational system was his confidence in the pattern. When the pattern demanded that there should be an element in a certain position, but no known element fit, he left a gap and predicted the properties of the missing element from the patterns around it. He predicted the existence of 3 such elements with specific densities, atomic weights, melting points, and chemical behaviors. Within 16 years, all 3 had been found. Gallium, discovered in 1875, matched his predictions for Eka aluminum almost exactly. Scandium in 1879, germanium in 1886. The table had predicted the existence of unknown elements and described their properties before anyone had ever seen them. That's not an organizational chart. That's a deep quantitative description of a pattern in nature. The question the table couldn't yet answer was why. Why did the properties repeat? What was it about sodium and potassium that made them so alike despite being so different in mass? Mendeleev didn't know. He'd found a map without knowing the territory the map described. The explanation was going to require a revolution in how physicists thought about matter itself. That revolution began in 1897 when J.J. Thomson discovered the electron. Thomson was studying beams of particles produced when electricity was passed through nearly evacuated glass tubes, cathode rays. He showed that these beams could be deflected by electric and magnetic fields, proving they were charged particles, and that the charge-to-mass ratio was the same regardless of what the electrodes or the gas in the tube were made of. These were particles that came from inside atoms themselves, whatever atoms were. They were negatively charged, vastly lighter than any atom, and apparently universal. Every material he tried produced the same particles. The atom had structure. It wasn't indivisible after all. Dalton's solid spheres were wrong. Inside the atom were smaller things. Since atoms were electrically neutral but contained negatively charged electrons, they had to contain something positively charged. Thomson proposed that the positive charge was spread out diffusely through the atom with electrons embedded in it, like raisins in a pudding, the plum pudding model, as it came to be known. It survived for about 14 years. In 1911, Ernest Rutherford and his team in Manchester fired tiny positively charged particles, alpha particles, which are helium nuclei, at a thin sheet of gold foil. Most of them went straight through, which made sense. If the positive charge was spread out diffusely, there'd be nothing to strongly deflect a passing particle. But a tiny fraction, about 1 in 8,000, bounced back almost the way they came, at angles greater than 90 degrees. Rutherford described this as the most surprising thing he'd ever witnessed in science, like firing artillery shells at tissue paper and having them bounce back and hit you. The only thing that could send a heavy particle bouncing straight back was a collision with something much more massive and concentrated. The positive charge, and essentially all the mass, had to be concentrated in a tiny, dense point at the center of the atom, the nucleus. Most of the atom was empty space. The electrons occupied a vast, mostly vacant volume around this tiny central core. The gold foil, when you thought about it, was almost entirely empty space. This was the Rutherford atom, a tiny, dense, positive nucleus orbited by electrons far out in mostly empty space, beautiful in its simplicity, and immediately obviously wrong about something crucial. According to the physics of the time, classical electrodynamics, an electron orbiting a nucleus would be constantly accelerating toward it, and accelerating charged particles continuously radiate energy as light. An electron should lose energy continuously, spiraling inward, and collapse into the nucleus in less than a nanosecond. Every atom in the universe should have collapsed long ago. You shouldn't exist. I shouldn't exist. Nothing should exist. The fact that atoms are stable was a crisis for physics. Niels Bohr, a young Danish physicist visiting Rutherford's lab in Manchester, proposed a partial resolution in 1913 that was audacious, almost to the point of absurdity. He simply declared that electrons could only exist in specific discrete energy levels around the nucleus, and that an electron in one of those levels didn't radiate. It just sat there, stable, without losing energy. An electron would only emit or absorb energy when it jumped from one level to another, and when it did, it emitted or absorbed a specific, precise quantity of energy, a photon, with a specific frequency. This explained something chemists and physicists had been puzzling over for decades: the line spectra of elements. When you heated a gas of hydrogen, for example, and looked at the light it emitted through a prism, you didn't see a continuous rainbow. You saw a specific set of bright lines at specific colors. Each element had its own pattern of lines, its own spectral fingerprint. Bohr's model predicted the hydrogen spectrum with extraordinary precision. The energy differences between Bohr's discrete levels corresponded exactly to the frequencies of the observed lines. But the model was held together by assumptions Bohr couldn't derive from any deeper principle. He had essentially said, electrons behave this way because if they did, the spectra would come out right. He was working backward from the observations, not forward from a theory. The deeper theory, the one that would explain why electrons could only occupy discrete energy levels and why they didn't radiate while in those levels, took another 12 years to arrive. What arrived in the 1920s was quantum mechanics, and it's the point in this story where the universe gets genuinely, irreducibly strange. The core insight emerged from multiple directions simultaneously. Louis de Broglie, in 1924, proposed that particles like electrons might have wave-like properties, that just as light had both wave and particle properties, matter might too. The wavelength of a particle would be inversely proportional to its momentum. This was a wild speculation with no experimental support at the time. Clinton Davison and Lester Germer experimentally confirmed it in 1927 by showing that electrons scattered off a nickel crystal produced a diffraction pattern, a pattern of interference fringes that you only get with waves. Electrons were interfering with themselves. They were waves. And almost simultaneously, Erwin Schrödinger wrote down an equation describing how these electron waves evolve in time, the Schrödinger equation. Werner Heisenberg developed an equivalent mathematical framework from a completely different direction. These turned out to be different mathematical representations of the same underlying theory, quantum mechanics. The framework that emerged said this: a particle, like an electron, doesn't have a definite position and velocity simultaneously. It has a wave function, a mathematical object that tells you the probability of finding the particle at any given position if you make a measurement. Before you measure, the particle doesn't have a specific position. It has a probability distribution, a smear of possibilities across space. When you measure, the wave function collapses to a specific outcome, and you find the particle at a specific place. But before the measurement, the question of where exactly the electron is has no answer. Not because we don't know the answer, because there isn't one. Heisenberg formalized this as the uncertainty principle. The more precisely you know a particle's position, the less precisely you can know its momentum, and vice versa. This isn't a limitation of our instruments. It's a property of reality. Position and momentum are complementary observables, and nature simply doesn't allow them to both have definite values simultaneously. This is not intuitive. It doesn't match anything in everyday experience, but it is what the universe is actually doing at small scales. What quantum mechanics gave chemistry was the concept of orbitals. An orbital is a probability distribution, the wave function, for an electron in a specific energy state around the nucleus, squared to give probability densities. It describes, spatially, where the electron is likely to be found. Orbitals aren't orbits. An electron in an orbital isn't going around the nucleus like a planet around the sun in a neat ellipse. It's more like a cloud of probability, a region of space where the electron is statistically concentrated. Different orbitals have different shapes, determined by quantum numbers that fall out of solving the Schrödinger equation for a nucleus. The lowest energy orbital around any nucleus is spherical. The next set of orbitals are dumbbell-shaped, pointing along the x, y, and z axis. Higher energy orbitals have more complex shapes, cloverleaf, donut, more exotic geometries. Each orbital can hold exactly 2 electrons, one spin up and one spin down, because of the Pauli exclusion principle, which says no 2 electrons in the same atom can have identical quantum states. The periodic table fell out of this directly, with no additional assumptions required. The first period has 2 elements, hydrogen and helium, because the first orbital, the spherical 1s orbital, holds exactly 2 electrons. The second period has 8 elements because the second shell has one s orbital and three p orbitals, totaling 4 orbitals holding 8 electrons. The third period also has 8. The fourth and fifth periods have 18 elements each, because the d orbitals kick in and add 5 more orbitals in each shell. Every length, every period, every group in the table reflects the filling of specific orbitals, and the filling order is exactly what you calculate from quantum mechanics. Mendeleev found a pattern without knowing why. Quantum mechanics explained why. From the ground up, the periodic table is a consequence of quantum mechanics applied to the structure of atoms. The chemical behavior of every element follows from how many electrons it has and how they're distributed across these orbitals. Which brings us to chemical bonding, and this is where we go from understanding isolated atoms to understanding molecules, the structures that chemistry actually builds. A chemical bond forms when two or more atoms come together in a way that lowers the total energy of the system. If the energy goes down, the bond is stable. If it doesn't, the atoms don't stick. It's as simple and as deep as that. The most common type of bond in chemistry, and the basis of almost all organic chemistry and biochemistry, is the covalent bond. When two atoms share electrons between them, both nuclei are attracted to the shared electrons simultaneously, and this mutual attraction is more stable than either atom alone. The hydrogen molecule is the simplest example. Each hydrogen atom has one electron and room for one more in its lowest orbital. When two hydrogen atoms approach, their electron clouds overlap. The two electrons can be shared between both nuclei, and the system reaches a lower energy, with the two atoms bonded together than with them separate. You've made a molecule. Carbon takes covalent bonding and does something unique with it. Carbon has 4 electrons in its outer shell and can form 4 covalent bonds simultaneously, pointing in different directions in 3-dimensional space. It can bond to other carbon atoms, creating chains and rings of arbitrary length and complexity. It can form single, double, or triple bonds. It can make flat ring structures where electrons are delocalized in a cloud above and below the plane of the ring. And because carbon-carbon bonds are strong but not impossibly strong, easy enough to break and reform under the right chemical conditions, stable enough to persist in ambient conditions, carbon can build structures of enormous variety and complexity that don't spontaneously fall apart. This is why carbon is the backbone of life. Silicon directly below carbon in the same column of the periodic table can also form 4 bonds, but silicon-silicon bonds are weaker, and silicon-oxygen bonds are so enormously strong that silicon tends to get locked into silicate rock structures, not dynamic molecular architectures. Carbon hits a sweet spot, strong enough to build stable structures, flexible enough to be chemically manipulated. The universe in using carbon as the basis for life wasn't being arbitrary. It was using the element with the right combination of properties for building complex, modifiable, information-rich structures. Ionic bonding is at the other end of the spectrum. Instead of sharing electrons, ionic bonding involves one atom giving up an electron entirely to another. This happens when one element holds its electrons very loosely. The alkali metals, like sodium and potassium, which have just one electron in their outer shell that takes very little energy to remove, and another element desperately wants one more electron to complete its outer shell, the halogens like chlorine and fluorine. When sodium meets chlorine, the electron moves completely from sodium to chlorine. Sodium becomes a positive ion, chlorine a negative ion, and opposite charges attract powerfully. Table salt sodium chloride is the product. It forms not as individual molecules, but as a continuous crystal lattice, a three-dimensional grid of alternating positive and negative ions, with each sodium surrounded by 6 chloride ions and vice versa. To melt it, you have to break millions of these attractions simultaneously, which is why salt melts at over 800 degrees Celsius. Metallic bonding is related to ionic bonding, but different enough to deserve mention. In a metal, the atoms release electrons into a shared sea, a cloud of electrons that moves freely through the entire metallic structure, while the positive ions sit in a regular lattice. This electron sea is why metals conduct electricity, apply a voltage, and the electrons flow. It's why metals are ductile. The positive ions can slide past each other, while the electron sea maintains the bonding. It's why metals are shiny. The free electrons can absorb and re-emit photons across a wide range of frequencies. Hydrogen bonding deserves particular attention because it's responsible for properties that make life possible. A hydrogen bond is weaker than a covalent or ionic bond. It's more of an attraction than a bond in the strong sense, but it's persistent enough to structure matter in important ways. It occurs when a hydrogen atom is covalently bonded to a very electronegative atom like oxygen or nitrogen. The electronegative atom pulls the electron cloud so strongly toward itself that the hydrogen nucleus, which is just a bare proton with no electron shielding on the side facing away from its bonded atom, is partially exposed and carries a partial positive charge. That exposed proton can then be attracted to lone pairs of electrons on another electronegative atom nearby. In liquid water, every molecule can form hydrogen bonds with several neighbors simultaneously, creating a continuously shifting dynamic network. These bonds break and reform constantly as molecules move and rearrange. But at any given moment, every water molecule is engaged in several of them. This network gives water properties that are anomalous for a molecule of its size. Pure van der Waals forces, the weak attractions between any polarizable molecules. On a molecule as small as water would predict it should be a gas at room temperature, like hydrogen sulfide, which has a similar structure. Water should boil around -80 degrees Celsius. It boils at 100 degrees. The hydrogen bonding network is responsible for that entire difference, and that difference is why liquid oceans exist on Earth, and why life as we know it can exist in them. Ice is another consequence of hydrogen bonding worth noting. When water freezes, the molecules form a hexagonal crystal structure with each molecule hydrogen bonded to 4 others in specific geometries. This open structure is less dense than liquid water, which is why ice floats. In almost every other substance, the solid is denser than the liquid. Water is anomalous, and anomalously, this anomaly is biologically crucial. If ice sank, ponds and lakes would freeze from the bottom up, potentially freezing solid in winter and killing everything in them. The ice floats, forms an insulating layer, and protects the liquid water underneath. Fish survive winter because of the hydrogen bond. Once you have molecules, the next question is, what happens when they meet each other, react, and produce new molecules, and whether or why they do? This is thermodynamics. Thermodynamics is one of those fields that sounds dry and technical, but is actually a story about something profound, the direction of time, and why the universe tends toward some states rather than others. The Industrial Revolution, which was driving rapid economic and social change in the early 19th century, also created an urgent practical need to understand how efficiently heat could be converted into mechanical work. Steam engines were everywhere, and engineers needed to know to their theoretical limits. The attempt to answer that practical question produced one of the deepest frameworks in all of science. The first law of thermodynamics is conservation of energy. Energy can be created or destroyed. In a chemical reaction, the energy stored in chemical bonds either gets released to the surroundings or absorbed from them, but the total doesn't change. Reactions that release heat to the surroundings, burning wood, dissolving certain salts, are exothermic. Reactions that absorb heat from the surroundings are endothermic. The amount of heat exchanged at constant pressure is what chemists call the enthalpy change of the reaction. But enthalpy alone doesn't determine which way reactions go. The second law, the one about entropy, does the rest. Entropy is worth spending time on because it's genuinely misunderstood in popular discourse. You'll often hear it described as disorder, and there's something to that, but the real definition is more specific and more interesting. Entropy is a measure of the number of microscopic configurations, the number of different ways you could arrange the atoms and molecules of a system that are consistent with its macroscopic state. A gas has high entropy because there are an astronomically large number of ways to arrange gas molecules in a container. A crystal has low entropy because the molecules are locked into specific positions The second law says that the total entropy of the universe, system plus surroundings, always increases in any spontaneous process. Systems naturally move from states of fewer possible configurations to states with more. Heat flows from hot to cold because the hot to cold direction increases the number of ways the total energy can be distributed across both objects. A drop of dye spreads through water because the spread out state has vastly more possible configurations than the concentrated state. Gases expand to fill their containers for the same reason. Josiah Willard Gibbs, an American physicist working in obscurity in New Haven in the 1870s, largely unrecognized in his lifetime, celebrated in retrospect as one of the most important scientists of the 19th century, combined enthalpy and entropy into a single quantity. The Gibbs free energy, G, equals the enthalpy H minus the temperature T times the entropy S. The change in Gibbs free energy for a process tells you directly whether that process is spontaneous. If the change in Gibbs free energy is negative, the process is spontaneous. It proceeds without requiring work to push it forward. If the change in Gibbs free energy is positive, the process is not spontaneous. It won't proceed unless you put energy in from outside. At equilibrium, the change in Gibbs free energy is zero. The equation for Gibbs free energy, where the change in G equals the change in H minus temperature times the change in S, is one of the most powerful tools in all of science. It encompasses both the tendency toward lower energy, negative enthalpy change, and the tendency toward more possible configurations, positive entropy change, and it shows that temperature determines which effect dominates. At low temperatures, enthalpy dominates. Systems tend toward their lowest energy states. At high temperatures, entropy dominates. Systems tend toward their most disordered states. This explains why ice melts above 0 Celsius. The entropy gain from liquid water is large enough that at temperatures above 0, the temperature times entropy term makes the Gibbs free energy change negative, and melting is spontaneous. Below 0, the entropy gain isn't enough, and the lower energy of ice wins. The phase transition happens at exactly the temperature where the Gibbs free energy change crosses 0, where the two effects exactly balance. It explains why proteins fold into specific three-dimensional structures. The loss of conformational entropy from going from a floppy chain to a compact folded structure is offset by the energy gain from forming hydrogen bonds, van der Waals contacts, and the favorable entropy gain in the surrounding water from burying hydrophobic groups away from it. It explains how living systems can build highly ordered, low entropy structures without violating the second law. They export entropy to their surroundings in the form of heat. Life runs continuous chemical reactions that release heat increasing the entropy of the environment by more than the entropy of the local biological structure decreases it. The total entropy of the universe still increases. Life doesn't violate thermodynamics. It uses thermodynamics. Electrochemistry is another branch that deserves mention here because it's everywhere in modern life and sits at a particularly interesting interface between chemistry and physics. An electrochemical reaction is a chemical reaction in which electrons are transferred between substances. An oxidation-reduction reaction or redox reaction. If you can separate the two half reactions with oxidation happening at one electrode and reduction at another and connect them by a wire, the electron transfer can power an electrical current. That's a battery. Alessandro Volta built the first battery in 1800, stacking alternating discs of zinc, brine-soaked cloth, and silver. He was trying to understand why a frog's leg muscle twitched when two different metals touched it, and he realized the metals were generating electricity through a chemical reaction. Michael Faraday, working in London in the 1830s, showed that the amount of substance deposited or dissolved in an electrochemical reaction was precisely proportional to the amount of electric charge passed, a relationship now called Faraday's laws of electrolysis. This quantitative link between chemistry and electricity was another step toward understanding matter at a deeper level. The modern lithium-ion battery, which powers essentially all portable electronics and electric vehicles, is an electrochemical device of considerable sophistication. Lithium ions move between the anode and cathode through the electrolyte during charge and discharge, storing and releasing energy in the form of the chemical potential difference between the lithiated and delithiated electrode materials. The specific choice of electrode materials, the electrolyte, the separator, all involve trade-offs between energy density, power density, safety, cycle life, and cost that have occupied materials chemists for decades. Battery performance is a chemistry problem, and it's one of the most practically consequential chemistry problems being worked on right now. Chemical kinetics, the study of how fast reactions go, is where thermodynamics meets the real world's inconvenient impatience. Thermodynamics tells you what can happen based on the free energy differences between starting materials and products. Kinetics tells you what actually happens based on the rate at which reactions proceed. The two can be completely decoupled. Diamond is thermodynamically unstable with respect to graphite. Graphite has lower free energy at ambient conditions, but diamonds persist essentially forever because the kinetics of diamond to graphite conversion are impossibly slow. Gasoline in air is thermodynamically unstable, but it doesn't burst into flame without a spark because the kinetics of combustion require an initial input of activation energy. Activation energy is the energy barrier a reaction has to climb over before it can proceed. Even if the products are more stable than the reactants, even if the reaction is thermodynamically favorable, the reacting molecules have to first reach a high energy transition state, a configuration where old bonds are partially broken and new bonds are partially formed. Getting to that transition state costs energy. At lower temperatures, fewer molecules have enough energy to climb that barrier. At higher temperatures, more do. This is why heating speeds up reactions exponentially, following the Arrhenius equation that the Swedish chemist Svante Arrhenius worked out in 1889. Catalysts lower the activation energy by providing an alternative pathway to the transition state. They participate in the reaction, sometimes forming temporary intermediate compounds with the reactants, but are regenerated at the end, so they're not consumed. A catalyst doesn't change where a reaction ends up thermodynamically. It just changes how easily it can get there. A good catalyst can make a reaction that would take years happen in seconds. Heterogeneous catalysis, where the catalyst is a solid and the reactants are gases or liquids, drives most of the industrial chemical processes that keep the modern world running. The Haber-Bosch process, where nitrogen gas and hydrogen gas combine to make ammonia over an iron catalyst, is the single most important industrial chemical reaction in human history. Nitrogen is about 78% of the atmosphere, but most living things can't use nitrogen gas directly. They need nitrogen in a fixed form, combined with hydrogen in ammonia, or oxidized to nitrate. Before the Haber-Bosch process, the only sources of fixed nitrogen were natural biological nitrogen fixation by bacteria and the slow accumulation of guano and saltpeter deposits. Both were limited and increasingly inadequate for a growing human population. Fritz Haber worked out the chemistry of nitrogen fixation in 1909, working with Carl Bosch to scale it up to industrial production. The ammonia produced then becomes fertilizer, and fertilizer allowed agricultural yields to grow fast enough to feed a world population that more than doubled in the 20th century. The estimate that about half the nitrogen atoms currently in human bodies came through the Haber-Bosch process isn't hyperbole. Billions of people are alive because this reaction was figured out and scaled up. It's also true that Haber used his chemistry skills to develop poison gas weapons in the First World War, and he supervised the deployment of chlorine gas at Ypres in 1915. His wife Clara, herself a chemist, was so opposed that she shot herself the night of the victory celebration he threw at their Berlin home, roughly 9 days after the Ypres attack. He left for the Eastern Front the next morning. Chemistry's power is not ethically neutral, and Haber's career makes that uncomfortable truth impossible to ignore. Enzyme catalysis in biological systems operates on principles that are fundamentally similar to heterogeneous catalysis, but with a sophistication that industrial catalysts still can't match. Enzymes are protein molecules with precisely shaped active sites that bind specific reactant molecules, their substrates, in exactly the right orientation and provide an environment that lowers the activation energy for a specific reaction. The specificity is extraordinary. An enzyme typically catalyzes exactly one reaction, or a very small class of related reactions, while ignoring everything else in the cellular environment. They operate at body temperature, in water, with no toxic solvents or extreme pressures. The rates they achieve are often millions or billions of times faster than the uncatalyzed reaction. Industrial chemists look at enzymes with a mixture of admiration and envy. Let's talk about acids and bases, because they're everywhere and the chemistry behind them is more interesting than it might seem. An acid, in the Brønsted-Lowry definition that's most commonly used in modern chemistry, is a species that donates a proton, a hydrogen ion, to another species. A base accepts a proton. When hydrochloric acid dissolves in water, it donates a proton to a water molecule, producing a hydronium ion and a chloride ion. This happens almost completely. Strong acids like hydrochloric acid donate their proton nearly every time they encounter water. Weak acids like acetic acid, the acid in vinegar, donate their proton only about 1% of the time. The extent of proton donation determines acid strength. The pH scale, running from 0 to 14, measures hydrogen ion concentration on a logarithmic scale, with each unit corresponding to a 10-fold change in concentration. Pure water has a pH of 7. It's neutral because it produces equal numbers of hydrogen and hydroxide ions through the autoionization of water. Below 7 is acidic, above 7 is basic. Battery acid sits around 0, lemon juice around 2, black coffee around 5, blood at 7.4, bleach around 12, drain cleaner around 13. The fact that blood is maintained at almost exactly pH 7.4 is not an accident. Enzymes and proteins in your body are exquisitely sensitive to pH. Small changes in the hydrogen ion concentration change how they fold, how they bind their substrates, how active they are. Your body runs an elaborate set of chemical buffering systems to resist changes in blood pH. The carbonate buffer system, a balance between dissolved carbon dioxide, carbonic acid, bicarbonate ions, and the rate of breathing, is the primary one. When blood pH starts to drop, you breathe faster, blowing off carbon dioxide, which shifts the equilibrium and raises pH back up. The chemistry of respiration and the chemistry of acid-base balance are directly coupled. Acid-base chemistry runs through industrial processes, through food chemistry, through environmental chemistry, through virtually every wet chemistry process that happens in any living organism. Understanding it quantitatively, being able to calculate the pH of a solution, predict how it changes when you add something to it, understand how buffer systems work, is one of the core skills that general chemistry courses are trying to build, not because pH calculations are intrinsically interesting, but because the underlying principles apply everywhere. Le Chatelier's principle governs equilibria of all types, including acid-base equilibria. If you disturb a system at equilibrium by adding reactants or removing products, by changing temperature or pressure, the system shifts to partially oppose the disturbance. This is why industrial processes can be engineered to drive reactions toward desired products, change the conditions, and the equilibrium shifts. Increase the pressure on a reaction that produces fewer moles of gas than it consumes, and you drive it toward products. Remove a product as it forms, and you keep pulling the reaction forward. Le Chatelier's principle is the industrial chemist's steering wheel. Organic chemistry is where chemistry becomes the language of life, of medicine, of materials, of essentially everything that involves carbon atoms, and carbon atoms are in almost everything important. The unique position of carbon in chemistry comes from a specific combination of properties. Carbon sits in the middle of the periodic table, in group 14, meaning it neither strongly wants to give away its 4 outer electrons, nor strongly wants to take 4 more. Instead, it shares. It forms 4 covalent bonds, pointing toward the 4 corners of a tetrahedron in 3-dimensional space. It bonds to other carbons readily and stably. It can form single bonds, double bonds, and triple bonds. It can form chains, branches, rings. It can form polycyclic ring systems of extraordinary geometric complexity. And because organic molecules can be so structurally diverse, the number of distinct organic molecules that can exist is effectively unlimited. Millions of distinct compounds have been characterized, and the vast majority of possible organic structures have never been made. The simplest organic compounds are the hydrocarbons, just carbon and hydrogen. Methane, the simplest, is what natural gas mostly consists of. 1 carbon, 4 hydrogens, nothing else. Ethane is 2 carbons, 6 hydrogens. Keep adding carbons and you get propane, butane, pentane, a series of straight-chain alkanes that are gases and liquids at room temperature. Longer chains, octane, hexadecane, are the components of gasoline and diesel fuel. The hydrocarbons are chemically unreactive with most things, which is why you can store them in tanks, but they burn in oxygen and release large amounts of energy from the breaking of carbon-hydrogen and carbon-carbon bonds, which is why they power vehicles and heat buildings. The chemistry gets more varied and interesting once you start adding other elements to the carbon skeleton. Add an oxygen connected to a hydrogen, a hydroxyl group, and you have an alcohol. Ethanol, the compound in alcoholic drinks, is a 2-carbon chain with a hydroxyl group. Methanol, the poisonous one, is a 1-carbon chain with hydroxyl. The properties of an alcohol are very different from the corresponding hydrocarbon. Alcohols are polar. They form hydrogen bonds. They dissolve in water. The carbonyl group, a carbon double bonded to an oxygen, appears in aldehydes, ketones, carboxylic acids, esters, and amides, and each of these functional group classes has characteristic reactivity. Aldehydes and ketones react with various nucleophiles. Carboxylic acids donate protons and can form esters and amides through condensation reactions. Amides are particularly important because the peptide bonds linking amino acids in proteins are amide bonds. The chemistry of proteins is largely the chemistry of amide formation and hydrolysis. Named reactions are a feature of organic chemistry that students often find overwhelming, but they tell a story about the development of the field. When Aldo, Diels-Alder, Grignard, Wittig, and hundreds of other chemists each worked out a specific, reliable way to form a specific type of bond or functional group under specific conditions, each discovery became a tool in the organic chemist's kit. Modern synthesis of complex molecules, drugs, natural products, materials draws on this accumulated toolkit, combining reactions in sequences that build up molecular complexity step by step. A synthesis of a complex drug might involve 20, 30, 40 steps, each carefully chosen to add the right piece in the right place without disrupting what's already there. It's an art as much as a science, and the best synthetic chemists are capable of a kind of molecular engineering that's almost architectural in its spatial complexity. The discovery in 1828 by Friedrich Böhler that urea, a compound produced in the body and excreted in urine, could be synthesized from purely inorganic starting materials, was a conceptual bombshell. Vitalism, the idea that organic compounds contain some vital force only living things could provide, had been a major intellectual constraint. Wöhler's synthesis showed that chemistry in the lab and chemistry in the body were operating by the same rules. The implications took decades to fully sink in, but they eventually produced organic chemistry as a discipline oriented toward creating compounds of biological relevance, drugs, dyes, polymers, agrochemicals. William Perkins' accidental discovery of Mauveine, the first synthetic dye in 1856, made while an 18-year-old student was trying to synthesize quinine from coal tar, launched the synthetic dye industry, and then, almost immediately, the pharmaceutical industry. The German chemical companies that dominated dye synthesis in the late 19th century also pioneered the systematic synthesis of pharmaceuticals. Bayer, famous for aspirin, started as a dye company. The infrastructure of organic synthesis built to make dyes was redirected toward drugs, and a combination of industrial scale synthesis and increasingly systematic exploration of what different molecular structures did in biological systems produced the first century of modern medicine. The story of how chemists came to understand that organic chemistry and biology were running on the same rules, that life was chemistry, is the story of biochemistry. And it's one of the most exciting in all of science. Proteins were known to be large molecules made of amino acids by the late 19th century. There are 20 standard amino acids, each with the same core structure, a carbon atom with an amino group and a carboxylic acid group attached, plus a variable side chain that's different for each, but with different side chains that give them different properties. Some are hydrophobic, some are hydrophilic, some carry charges, some can form covalent crosslinks, some are rigid, some are flexible. The sequence of amino acids in a protein chain, the primary structure, determines everything about the protein. Proteins fold spontaneously and rapidly from their extended chain conformation into precise three-dimensional structures, globular enzymes, fibrous structural proteins, transmembrane channels, receptor proteins. The folding is driven by the same forces that govern all of chemistry. Hydrogen bonds form between backbone groups. Hydrophobic side chains cluster in the interior away from water. Charged side chains are positioned to interact with their partners. Van der Waals forces accumulate between closely packed atoms. The result is a specific, reproducible, three-dimensional structure that's the same for every copy of the protein with the same sequence. The function of a protein depends critically on its structure. Enzymes have active sites, cavities, or surfaces with precisely positioned chemical groups that bind specific substrate molecules and catalyze specific reactions. If you change a single amino acid in the active site, the enzyme often stops working. The chemistry is exquisitely position-specific at the atomic scale. Understanding the code connecting DNA, short for deoxyribonucleic acid, to protein structure, was the central problem of molecular biology in the 1950s and 60s, and it was solved through a combination of chemistry and physics and biology working together more closely than they had before. Rosalind Franklin used X-ray diffraction, a technique where X-rays scatter off the regular structure of a crystal, and the scattering pattern tells you the three-dimensional arrangement of atoms to produce high-quality images of DNA fibers. The patterns in her images, including the famous photograph known as Photo 51, showed a helical structure with specific dimensions. James Watson and Francis Crick, using these data along with knowledge of the chemistry of the DNA bases and model building, worked out the double helix structure in 1953. The two strands of the helix were held together by hydrogen bonds between complementary base pairs, adenine with thymine, guanine with cytosine. The sequence of bases along one strand uniquely determined the sequence along the other, which immediately suggested the mechanism of replication. Unwind the helix, use each strand as a template to build a complementary strand, end up with two identical double helices. The genetic code, the specific mapping from tree-based sequences in DNA to amino acid sequences in proteins, was worked out through painstaking biochemical experimentation through the early 1960s. Marshall Nirenberg and Har Gobind Khorana shared the Nobel Prize for this work. By 1966, the entire code was known. 64 three-letter codons, coding for 20 amino acids and 3 stop signals. The code was almost universal across all life on Earth. The same codons meant the same amino acids in bacteria, plants, and humans, implying that all life shared a common ancestor in which the code was established. This universality is one of the deepest facts in biology, and it's a chemical fact at its root. Life on Earth is running one molecular system, DNA, then ribonucleic acid, which chemists call RNA, then protein, and the system works because of specific chemical complementarity, specific geometric fits between molecules that allow information to be copied, read, and translated. The structure of the ribosome, the enormous molecular machine made of protein and RNA that reads messenger RNA and builds protein chains, was worked out by X-ray crystallography in the early 2000s, winning the Nobel Prize in Chemistry in 2009. The ribosome is chemistry doing computation. It reads a molecular message and outputs a molecular product with an error rate of about 1 in 10,000 amino acids. Your cells contain millions of ribosomes, collectively making proteins around the clock. Everything structural and functional in a living cell is the product of protein synthesis on ribosomes, guided by genetic information in DNA. CRISPR, Cas9 gene editing, which has transformed molecular biology in the last decade, is at its heart a chemistry story. The Cas9 protein is a molecular scissors that cuts DNA at a sequence specified by a guide RNA molecule. The guide RNA carries a sequence complementary to the target DNA and base pairing between the guide RNA and the target positions the Cas9 precisely on the genome, where it cuts both strands. The cell's repair machinery then either destroys the cut gene, knocking it out, or incorporates a template sequence you've provided, effectively editing the genome with single-letter precision. This molecular precision comes from the chemistry of base pairing, the same chemistry that makes DNA replication work and that Crick and Watson read from Franklin's X-ray images in 1953. The therapeutic implications are profound. Clinical trials are already underway using CRISPR to treat sickle cell disease caused by a single point mutation in the hemoglobin gene, as well as certain cancers and other genetic conditions. The chemistry that lets a guide RNA of about 20 bases find and bind to a specific sequence in a genome of 3 billion base pairs is the same hydrogen bond chemistry that governs water structure and protein folding. The specificity of base pairing, a chemical property, is the engine of genetic medicine. Let's go somewhere that demonstrates chemistry's dual nature, its power to create and its power to destroy, because no honest account of chemistry leaves this out. The story of nuclear chemistry begins in a basement laboratory in Paris in 1896. Henri Becquerel had left a packet of uranium salts sitting on a wrapped photographic plate in a drawer during a period of cloudy weather. He had intended to study phosphorescence using sunlight, but the overcast weather prevented that. When he eventually developed the plate, expecting to find nothing, he found it had been exposed. There were images of the uranium crystal shapes. The uranium was emitting invisible radiation on its own, without any external energy input, and this radiation was strong enough to expose photographic film through its wrapping. He discovered radioactivity, the spontaneous emission of radiation from atomic nuclei. Marie Curie took this observation and built a career on it. She and her husband, Pierre Curie, spent years doing the brutally laborious chemical work of isolating radioactive substances from ore. Processing literally tons of uranium ore, working in crude conditions in a leaky shed, they identified two new elements: polonium, named after her homeland Poland, and radium, which was so intensely radioactive it glowed in the dark. She kept tubes of radium and polonium on her desk and in her coat pockets. She died in 1934 of aplastic anemia, her bone marrow destroyed by decades of radiation exposure. Her personal notebooks are still so radioactive that researchers who need to consult them must sign liability waivers and wear protective equipment. The pages are a primary source and a radiation hazard simultaneously. Ernest Rutherford classified the types of radiation and showed they were actually three different phenomena: alpha particles, which were helium nuclei, beta particles, which were electrons, and gamma rays, which were high-energy photons. Each type of decay transformed the emitting atom into a different element. Uranium decayed into thorium, which decayed into radium, which decayed down a long chain into stable lead. The elements were transforming into each other, the alchemist's dream, happening naturally, but through a mechanism utterly unlike anything they'd imagined, and impossible to control or induce by any chemical means. The neutron, discovered by James Chadwick in 1932, unlocked the next step. Because it carries no charge, a neutron can penetrate an atomic nucleus without being repelled by the positive charge. Enrico Fermi in Rome began systematically bombarding elements with neutrons in 1934, seeing what happened. When he bombarded uranium, he got confusing results, products that didn't fit simple transmutation. He and his team misidentified what they were seeing. Otto Hahn and Lise Meitner, working in Berlin, continued the work over the next 4 years with more careful analysis. In 1938, after Meitner had fled Nazi Germany, she was Jewish, and was working in Sweden, Hahn sent her the results of a new experiment that deeply puzzled him. The products of neutron bombardment of uranium were barium and krypton, elements roughly half the mass of uranium. Something very different from simple transmutation was happening. Meitner and her nephew, Otto Frisch, worked out what it was. The uranium nucleus, upon absorbing a neutron, became unstable and split in two, like a liquid drop stretching until it divides. They calculated the energy released using Einstein's famous equation, where energy equals mass times the speed of light squared. The mass of the two products was very slightly less than the mass of the original uranium plus neutron, and that tiny mass difference, multiplied by the square of the speed of light, came out to about 200 million electron volts of energy per fission event. By the standards of chemical reactions, this is an almost incomprehensible amount of energy. A typical chemical reaction releases a few electron volts. Nuclear fission releases tens of millions of times more per atom. The chain reaction possibility was immediately obvious to physicists who saw the fission results. Each uranium 2, 3, 5 fission produced 2 or 3 neutrons, which could each trigger additional fissions, which produced more neutrons in an exponentially branching chain. If you had enough uranium, 2, 3, 5, above the critical mass, the chain reaction could proceed in a fraction of a second, releasing an enormous amount of energy simultaneously. Leo Szilard, a Hungarian-German physicist who had been thinking about chain reactions theoretically for years and had even patented the concept in 1934, grasped the implications immediately and was alarmed. He and Enrico Fermi, who had emigrated to the United States after his wife's relatives in Italy faced persecution, drafted a letter and convinced Einstein to sign it. The Einstein-Szilard letter went to President Roosevelt in 1939, warning that Germany might be pursuing a nuclear weapon and urging American research. That letter set in motion the Manhattan Project. The Manhattan Project involved over 130,000 people at its peak, spread across dozens of sites including Oak Ridge in Tennessee, Hanford in Washington State, and Los Alamos in New Mexico. The scientific director at Los Alamos was J. Robert Oppenheimer, coordinating the work of an extraordinary concentration of scientific talent. The engineering challenge, building atomic bombs using materials and processes that had never existed before, at scales that had never been attempted, on a timeline measured in years rather than decades, was unlike anything that had been tried in human history. Two different designs were pursued simultaneously. The gun-type bomb used at Hiroshima worked by firing one subcritical mass of uranium, 2, 3, 5, into another, instantly creating a supercritical mass and triggering a chain reaction. The implosion-type bomb used at Nagasaki surrounded a subcritical sphere of plutonium, 239, with precisely shaped explosive lenses that detonated simultaneously, compressing the sphere to supercritical density. The explosive implosion design was technically more difficult, but necessary for plutonium, which would pre-detonate in the simpler gun-type design. The Trinity test, conducted in the New Mexico desert on July 16, 1945, produced an explosion equivalent to about 21,000 tons of conventional explosive. Oppenheimer later said that the line from the Bhagavad Gita came to mind. "Now I am become death, the destroyer of worlds." 3 weeks later, a uranium bomb destroyed Hiroshima. 3 days after that, a plutonium bomb destroyed Nagasaki. The total death toll from the immediate blasts and subsequent radiation sickness was somewhere between 129,000 and 226,000 people, the vast majority civilians. The post-war nuclear age was shaped by the intersection of this terrible capability and the peaceful applications of the same physics. Nuclear reactors, which use controlled chain reactions, slowed by moderators, regulated by control rods, never allowed to go supercritical, to produce heat and generate electricity, grew directly from Fermi's first self-sustaining pile, built in a squash court under the bleachers of the old Stagfield football stadium at the University of Chicago in December 1942. Today, nuclear power provides about 10% of global electricity with no direct carbon emissions during operation. France gets about 70% of its electricity from nuclear power. The technology has had accidents: 3 Mile Island, Chernobyl, Fukushima, but the overall safety record per unit of energy produced is better than fossil fuels. Nuclear fusion, the process that powers the sun, where light nuclei fuse to form heavier ones, has been the perennial promise of unlimited clean energy. Fusion of deuterium and tritium produces helium and a neutron, plus about 17 mega-electron volts of energy. The fuel, hydrogen isotopes, is effectively inexhaustible. But fusion requires temperatures of tens of millions of degrees to overcome the electrostatic repulsion between positively charged nuclei and give them enough kinetic energy to fuse. No material container can hold plasma at those temperatures. Magnetic confinement, using strong magnetic fields to keep the plasma away from the walls of the reactor, has been the dominant approach. Inertial confinement, using powerful lasers to compress a small fuel pellet so rapidly that it ignites before it can fly apart, is the other. In December 2022, the National Ignition Facility in California achieved fusion ignition for the first time in history. The energy output from fusion exceeded the energy delivered by the lasers triggering it. A milestone, but still far from a viable power plant, which would need to be more efficient by orders of magnitude and run continuously rather than in pulses. Now, let's look at what chemistry builds in the world. Start with medicine, because medicine is where chemistry's power to reshape human lives is most directly felt. Every drug you've ever taken is a molecule. Not a mysterious potion, not a category, a specific, precisely characterized molecule with a specific three-dimensional structure, a specific set of interactions with biological targets, and specific behavior in the body regarding absorption, distribution, metabolism, and excretion. The aspirin molecule, acetyl salicylic acid, works by irreversibly modifying cyclooxygenase enzymes, preventing them from synthesizing prostaglandins and thromboxans, which are the mediators of inflammation and platelet aggregation. That's why aspirin reduces fever, inflammation, and pain, and why a low daily dose reduces the risk of heart attack. Different doses hitting the same chemistry at different points. Penicillin, discovered by Alexander Fleming in 1928 when he noticed a mold-killing bacteria on a petri dish, works by blocking transpeptidase enzymes that bacteria use to cross-link the peptidoglycan in their cell walls. When bacteria grow and divide in the presence of penicillin, they try to build new cell walls but can't cross-link them properly, and the new cells burst from internal osmotic pressure. The drug selectively kills bacteria because human cells don't have peptidoglycan cell walls and don't use transpeptidases. The selectivity, the difference between what the drug does to the pathogen versus what it does to you, comes from a difference in chemistry between bacterial and human biology. HIV antiretrovirals work by blocking one of several enzymes the virus uses to copy its own genetic material inside human cells. Reverse transcriptase converts the viral RNA genome into DNA, which is then inserted into the host cell's genome. Integrase carries out that insertion. Protease cleaves viral proteins from their initial long precursor form into functional individual proteins. Drugs blocking each of these steps have been developed, and combination therapy using drugs hitting multiple targets simultaneously has transformed HIV from a death sentence to a manageable chronic condition. Each drug is a specific molecule designed or discovered to fit into the active site of a specific viral enzyme and block its function. Statins, the most widely prescribed class of drugs in the world, work by blocking the rate-limiting enzyme in the liver's cholesterol synthesis pathway. When the liver can't make as much cholesterol internally, it upregulates the low-density lipoprotein receptors on its surface to take more from the blood. Blood low-density lipoprotein cholesterol drops. Heart attack risk drops. The entire therapeutic effect flows from one enzyme's kinetics being changed by a molecule that looks like the enzyme's natural substrate but sticks tighter and doesn't let go. The drug development pipeline that produces these medicines is long and expensive because the chemical problem is hard. A drug candidate has to get into the body through the gut or through injection, survive the acidic stomach and the liver's metabolic enzymes, travel through the bloodstream to the right tissue, cross cell membranes if necessary, find the right molecular target among millions of similar proteins, interact with that target in the right way, and then be metabolized into non-toxic breakdown products that can be excreted. Getting all of those properties right simultaneously in a molecule that can also be synthesized reliably and stored stably is enormously difficult. About 90% of drugs that enter clinical trials fail. The failures contain information. Chemistry learns from them, but they're expensive failures. AI is beginning to change this. Machine learning models train on millions of known drug-like molecules, and their properties are increasingly being used to suggest candidates that are likely to have the right combination of properties before synthesis. Generative models can design new molecular structures with specified target binding profiles. AlphaFold's solution to the protein folding problem means that the targets themselves, proteins whose three-dimensional structure was unknown, can now be characterized computationally. The combination of these tools is compressing the early stages of drug discovery in ways that will take years to fully understand, but are already producing results. Material science is equally chemistry-driven, though it tends to be less visible to most people. Plastics transformed the material world of the 20th century, and plastics are polymers, long chains of repeating chemical units. The first truly synthetic plastic, bakelite, was invented by Leo Baekeland in 1907 from phenol and formaldehyde. A century later, plastics are so embedded in modern life that imagining its absence requires effort. Every wire has plastic insulation. Every vehicle has plastic components. Every food package is plastic. Every electronic device is encased in it. The specific properties of each plastic, flexibility, rigidity, clarity, chemical resistance, melting temperature, follow from the specific chemistry of its polymer chains. Nylon, developed at DuPont in the 1930s, has chains formed by condensation reactions between diamines and diacids, producing amide bonds, the same bond type that links amino acids in proteins. The result is a semi-crystalline material with high tensile strength and a low melting point relative to inorganic materials, making it processable while tough in use. Teflon, discovered accidentally at DuPont in 1938, consists of carbon chains entirely surrounded by fluorine atoms. The carbon-fluorine bond is one of the strongest in organic chemistry, and the complete fluorination makes the surface chemically inert and extremely non-adhesive. Kevlar, developed in the 1960s, consists of chains of aromatic rings linked by amide bonds, forming a rigid, ladder-like structure that hydrogen bonds strongly between chains and packs into a highly ordered fiber that's extraordinarily strong for its weight. Silicon semiconductors are the basis of every electronic device in the modern world, and producing them is as much a chemistry problem as a physics problem. The purity requirements for electronic-grade silicon, parts per trillion of dopant atoms, are achievable only through elaborate purification chemistry. Building transistors at nanometer scales requires depositing precise thin films of specific materials using gas phase chemistry, removing material with specific etchants, and protecting areas with photosensitive polymers that change their chemistry when exposed to specific wavelengths of light. The photoresist chemistry is particularly sophisticated. The light-sensitive molecule undergoes a specific photochemical reaction that changes its solubility, allowing the pattern to be transferred to the underlying material. Every generation of smaller, faster transistors has required new chemistry. Let's talk about where chemistry sits right now, at the frontier between what's known and what's coming. Computational chemistry has gone from a specialty tool to a pervasive presence in chemical research over the last 3 decades. The key methods range from quantum mechanical calculations, solving approximate versions of the Schrödinger equation for molecules, to molecular dynamic simulations that track the positions and velocities of millions of atoms over nanoseconds or microseconds, to machine learning potentials that learn from quantum calculations and apply them at far larger scales. Density functional theory, developed in the 1960s by Walter Kohn and Liu Zhou-Sham, approximates the quantum many-body problem by working with the electron density distribution rather than the full wave function. It's still an approximation, but the exchange correlation functional, which describes the quantum mechanical effects not captured by classical electrostatics, is known exactly only in limiting cases. And in practice, density functional theory is accurate enough for most chemical applications, while being computationally tractable for molecules of moderate size. Kohn shared the Nobel Prize in Chemistry in 1998 for this work. Density functional theory is the workhorse of computational chemistry. Machine learning potentials are a newer development that represents a genuinely different approach. Instead of solving the quantum mechanics of a molecule approximately to find the forces on each atom, a machine learning potential learns the relationship between atomic configurations and energies from a large database of quantum calculations, and then predicts energies and forces for new configurations instantly. They're orders of magnitude faster than quantum calculations, while being nearly as accurate for the types of configurations they've been trained on. They've enabled molecular dynamics, simulations of protein folding, battery electrode materials, and complex reaction mechanisms that would have been computationally impossible a decade ago. The potential of quantum computers for chemistry is the next big thing, and it's approaching faster than many expected. The fundamental challenge is that simulating a quantum system on a classical computer requires exponentially increasing resources as the system size grows. A quantum computer stores information as quantum bits that can be in superpositions of 0 and 1 and can represent and manipulate quantum states directly. For chemical simulation, calculating the electronic structure of a molecule, the energy of a reaction, the binding affinity of a drug, a quantum computer with enough stable qubits could in principle do in seconds what a classical computer couldn't do in the age of the universe. In March 2026, IBM researchers used a quantum computer to characterize a chemically exotic molecule and prove properties that classical calculations couldn't reliably predict. The drug discovery industry is watching carefully, and the market for quantum computing in drug discovery is projected to grow from about $126 million in 2025 to nearly 640 million by 2035. Green chemistry, designing chemical processes to minimize waste, use safer materials, and reduce energy consumption, has evolved from a fringe concern to a mainstream priority in both industrial and academic chemistry. The 12 principles of green chemistry, articulated by Paul Anastas and John Warner in 1998, cover everything from preventing waste rather than treating it, to using renewable feedstocks, to designing chemicals to degrade after use. The chemical industry is one of the largest sources of industrial waste and energy consumption in the world, and the transition to greener processes is both an environmental imperative and, increasingly, an economic one. Greener processes are often simpler, cheaper to run, and produce less troublesome byproducts. Low chemistry, running reactions continuously in small tubes or channels rather than in large batch reactors, allows precise control of temperature, mixing, and reaction time that's difficult in batch processing. It reduces the volumes of hazardous materials in use at any time, lowers energy requirements, and often enables reactions that are impractical at large scale. The pharmaceutical industry has been particularly active in adopting flow chemistry, reducing both costs and environmental impact. Biocatalysis, using enzymes to carry out chemical reactions, is another green chemistry trend. Enzymes work in water, at room temperature, with no toxic solvents, and with exquisite selectivity that avoids side products. The number of industrial chemical transformations now being done enzymatically has grown enormously as enzyme engineering, modifying enzyme sequences to optimize their performance for non-natural substrates, has matured. Sitagliptin, a diabetes drug, is manufactured using a specifically engineered enzyme in a process that replaced a hazardous high-pressure hydrogenation with a benign biocatalytic step. The enzyme was designed computationally and optimized through directed evolution, essentially doing chemistry's own iterative improvement process on the enzyme molecule. Let's step back and think about some of the bigger theoretical questions that chemistry sits at the center of, because this is where the science gets philosophically interesting. The origin of life is a chemistry problem, and it's one that remains genuinely open. At some point, roughly 4 billion years ago, on an early Earth that was very different from today, hotter, more volcanically active, bombarded by meteorites, with an atmosphere that contained essentially no free oxygen, chemistry that had previously been generating complex organic molecules, but nothing more crossed some kind of threshold. It started self-replicating. A chemical system began copying itself, not perfectly, but reliably enough that the copies outnumbered the errors. Evolution, driven by differential replication of variants, could begin. Biology started. We know the building blocks are not rare. In 1952, Stanley Miller working in Harold Urey's lab in Chicago, showed that amino acids form spontaneously when you pass electric discharges through a mixture of water, methane, ammonia, and hydrogen, an approximation of the early Earth's atmosphere. The experiment has been repeated many times with variations and always produces organic molecules including amino acids and nucleotide precursors. Amino acids have been found in meteorites. They form in space without any special conditions on Earth. Nucleobases, the building blocks of DNA and RNA, form similarly easily from simple starting materials. The raw ingredients for the chemistry of life are essentially everywhere in the universe, that there's chemistry happening at all. The problem is the gap between the ingredients and the system. Even the simplest possible living cell that we know of is an enormously complex network of hundreds of different molecules working together in a precisely coordinated way. There's no obvious path from amino acids in a pool to a self-replicating cell. The RNA world hypothesis proposes that RNA, which can both store genetic information like DNA and catalyze reactions like proteins, was the first molecule to achieve self-replication, and that DNA and proteins came later. RNA ribozymes that catalyze their own synthesis from simpler RNA fragments have been made in the lab, providing proof of concept, but the gap from there to a cell is still vast. Hydrothermal vents on the ocean floor have been proposed as the likely setting because they provide thermal and chemical gradients, mineral surfaces that can concentrate reactants, and continuous energy from the chemistry of sulfide minerals reacting with seawater. The chemistry at alkaline hydrothermal vents, where warm hydrogen-rich fluid meets cooler carbon dioxide-rich ocean water, mimics some aspects of early cellular metabolism, but demonstrating that the specific sequence of events that led from chemistry to life happened in this setting rather than in a warm pond in ice, on mineral surfaces, or in the atmosphere, hasn't been done. This is one of the questions that chemistry might answer in the coming decades, as synthetic chemistry, biochemistry, and geochemistry converge on it with increasingly powerful tools. Building a living system from scratch, starting with chemistry and arriving at something that replicates and evolves, would be the deepest result in the history of the subject. Emergence is a theoretical framework in chemistry that's worth understanding because it changes how you think about what chemistry is for. The concept is that when you go from atoms to molecules to complex chemical systems to cells to organisms, genuinely new properties appear at each level of organization, properties that cannot be predicted or explained purely by looking at the level below. You can't predict the hydrogen bonding network of liquid water from the quantum mechanics of isolated hydrogen and oxygen atoms, even in principle, without also understanding how water molecules interact with each other. You can't predict enzymatic catalysis from the properties of individual amino acids. You can't predict consciousness from the chemistry of neurons. This doesn't mean that physics underlies chemistry or that chemistry underlies biology in the sense of being a complete explanatory account of each. It means each level of organization introduces new concepts, new regularities, new causal structures that are real and important at that level and can't simply be reduced away to the level below. Chemistry is not physics in disguise. Biology is not chemistry in disguise. The reductionist account that says it's all just atoms is technically true and practically useless. What this means for chemistry as a discipline is that chemistry has its own level of explanation: molecular structure, reactivity, thermodynamics, kinetics, that is irreplaceable even in a world where we have complete quantum mechanics. The synthetic chemist designing a new drug candidate is thinking in terms of functional groups, binding affinities, metabolic stability, chemical concepts that live at a different level from electron wave functions. Both levels are necessary. Chemistry is the level where the universe's abstract quantum rules become materials with properties you can touch and use and build with. Astrochemistry is another frontier worth exploring. The interstellar medium, the gas and dust between stars, is not the sterile void it might seem. Over 200 distinct molecular species have been detected in space using radio astronomy, from simple diatomics like carbon monoxide and hydrogen cyanide to complex organics like ethyl formate and propylene oxide. Molecular clouds, where stars form, are dense enough to shield chemistry from ultraviolet radiation and are sites of active gas phase and surface chemistry. Amino acids, nucleobases, and other prebiotic molecules have been found in meteorites, demonstrating that these building blocks form in space through chemistry that has nothing to do with life. The carbon in your body was not on Earth when the Earth formed. It was made in stars, specifically in the helium-burning shells of red giant stars, where 3 helium nuclei fuse to form carbon in the triple alpha process. When those stars reached the end of their lives and exploded as supernovae or shed their outer layers as planetary nebulae, they dispersed that carbon into space. That carbon gathered in a new cloud of gas and dust. That cloud collapsed under gravity to form our sun and planets, and the carbon ended up in chemistry happening on the surface of this planet for 4 billion years, which eventually resulted in you watching this video. You are the universe's chemistry contemplating itself. Here's where we look forward, and I want to be honest about the difference between what seems likely and what's speculative. The near-term future of chemistry, the next 10 to 20 years, is probably going to be characterized by 3 things above all: the integration of AI into every stage of chemical research, the maturation of quantum computing for chemical simulation, and the chemistry of the energy transition. AI in chemistry is already transforming drug discovery, materials discovery, and synthesis planning. Language models trained on chemical literature can suggest synthetic routes and spot potential problems. Neural network potentials can run molecular dynamics simulations of systems that were previously too large for quantum calculations. Generative models are designing new molecules with specified properties: a protein that binds a specific target, a material with a specific band gap, a catalyst that converts a specific substrate. This isn't replacing chemists, but it's reshaping what chemists spend their time doing. The parts of the job that involve pattern recognition across large data sets are being done by computers. The parts that require physical intuition, experimental ingenuity, and knowing when the result doesn't make sense are still very much human. Quantum computing for chemistry is the technology that could make the biggest difference in the longest term. The molecules where quantum computing would add the most value are the ones where electron correlation, quantum mechanical effects that classical approximations handle poorly is most important. These tend to be transition metal complexes, which show up in biological catalysts, in nitrogen-fixing enzymes, in oxygen-evolving catalysts for solar fuel production. Getting the electronic structure of these molecules right is critical for designing better catalysts, and current classical methods are inadequate. A quantum computer with a few hundred reliable logical qubits could, in principle, calculate properties of these molecules that no classical computer can access. We don't have that yet, but the trajectory of quantum hardware improvements suggests it might arrive in the next decade. The chemistry of decarbonizing the energy system is urgent and enormous in scope. Better batteries with higher energy density and longer cycle life, cheaper, more stable perovskite solar cells to complement or replace silicon, catalysts for green hydrogen production by water electrolysis, and catalysts for nitrogen reduction to ammonia using renewable electricity rather than fossil methane. Direct air capture of carbon dioxide using solid sorbents or liquid amines, fuels made from captured carbon dioxide and renewable hydrogen, concrete alternatives that don't require calcining limestone and releasing carbon dioxide, building materials with embedded carbon from biomass. The whole material infrastructure of modern civilization runs on processes that emit greenhouse gases, and changing that infrastructure requires chemistry at every step. The blurring of chemistry and biology will continue, and this is probably where the most surprising things will happen. Synthetic biology is engineering cells with genetic circuits that don't exist in nature to produce valuable chemicals, detect disease, or perform logical operations inside the body. Bacteria have been engineered to produce insulin, artemisinin, specialty chemicals, biodegradable plastics, and in a proof of concept that raised immediate ethical concerns: complete opioid drugs. The distinction between living cells and chemical production systems is being eroded intentionally. Cell-free systems take this further. You can extract the cellular machinery, ribosomes, transfer RNAs, amino acids, all the components, and run protein synthesis in a test tube without living cells. This is already being used to produce proteins that cells themselves can't make efficiently, and to test genetic circuits before putting them into cells. The machinery of life is becoming laboratory equipment. Long term, the question of whether we can build a living system from chemistry from scratch, not by modifying existing life, but by assembling molecular components that have never been alive, remains open but is increasingly a target of serious research programs. If it's achieved, it will be the most profound result in the history of biology and chemistry, and it will collapse the distinction between the two in ways that make our current categories look primitive. The protein folding problem is solved in the sense that AlphaFold can predict the static structure of most proteins. But understanding how proteins fold dynamically, how they move and change shape as they function, how they interact with other proteins and with drugs in the complex environment of the cell, these are still open. The computational tools being developed to address them will have enormous consequences for drug design and for understanding disease. Predictions are tricky in science because the most important results are often the ones nobody saw coming. Nobody predicted the discovery of CRISPR in bacteria, or that it could be turned into a gene editor. Nobody predicted that a small English mold would produce the first antibiotic. Nobody predicted that coal tar, a waste product of the gas lamp industry, would give rise to the synthetic dye industry and then pharmaceutical chemistry. The history of chemistry is full of results that came from unexpected directions and had consequences that took decades to recognize. What we can say with some confidence is that chemistry is accelerating. The combination of massive datasets of chemical knowledge, AI to extract patterns from them, automation to generate experimental data faster than humans could, and quantum computing to access previously inaccessible theoretical predictions is creating a different kind of research practice. The exploration of chemical space, the vast territory of all possible molecules and materials, is going to happen faster in the next 30 years than it did in the previous 3 centuries. The diseases that currently have no effective treatment, Alzheimer's, various cancers, antibiotic-resistant infections, certain rare genetic disorders, are the most likely beneficiaries. The energy technologies that need new materials, better batteries, better photovoltaics, better fuel cells will get them faster. The materials that make possible the next generation of electronics, of structural engineering, of water purification, will be designed computationally and tested rapidly. And somewhere in all of that activity, something will be discovered that nobody currently expects, and it will seem, in retrospect, like it was obviously waiting to be found. before we get to the big picture, let's go somewhere that often gets skipped over in popular explanations of chemistry, but is worth spending real time on, because it sits at the precise boundary between the abstract world of atoms and the tangible world of materials we actually live in. That boundary is intermolecular forces. Everything you've heard about atoms and molecules so far is about what happens inside a molecule, the bonds holding atoms together. But molecules also interact with each other, and those interactions, weak, often invisible, operating over much shorter distances than covalent or ionic bonds, are responsible for whether a substance is a solid, a liquid, or a gas at any given temperature. They determine melting points and boiling points. They determine solubility. They determine why oil and water don't mix. They determine the consistency of butter versus the fluidity of cooking oil. They determine why a gecko can walk on a glass ceiling. If chemical bonds are the nouns of chemistry, intermolecular forces are the punctuation. Small, often overlooked, but structuring everything. The weakest intermolecular force is the London dispersion force, and understanding it requires thinking about electrons probabilistically rather than deterministically. At any given instant, the electrons in a molecule are not symmetrically distributed. They're somewhere specific, but where they are changes from moment to moment because quantum mechanics governs their behavior, not classical physics. At any instant, one side of a molecule might have slightly more electron density than the other, creating a tiny temporary dipole. That temporary dipole influences the electrons in nearby molecules, inducing a complementary temporary dipole in them, one that's attracted to the original. These interactions are incredibly short-lived and individually very weak. But molecules are never really alone. They're always surrounded by other molecules. And all of those tiny, fleeting, synchronized attractions add up. The astonishing thing about London dispersion forces is that they can, in large molecules, become the dominant intermolecular force, even when other interactions are present. A pair of chemists called this out beautifully with the comparison between trichloromethane and tetrachloromethane. Trichloromethane is highly polar. It has a strong permanent dipole because of its 3 electronegative chlorine atoms. Tetrachloromethane has no permanent dipole at all. The 4 chlorines are arranged symmetrically, canceling each other out. You might expect trichloromethane to have the higher boiling point because its permanent dipole-dipole interactions are stronger than mere London forces. But tetrachloromethane actually boils higher. Because it has more electrons, its London forces are stronger, and those stronger London forces outweigh the permanent dipole interactions of the smaller molecule. More electrons means more polarizability, means stronger temporary dipoles, means stronger London forces. This is why Long-chain hydrocarbons are liquids and solids at room temperature, while methane is a gas. The dispersion forces build as the chains get longer. Electronegativity is the property that ties all of this together, and it was the brilliant insight of Linus Pauling, working in the 1930s and still going strong into the 1990s. To quantify it systematically, electronegativity is a measure of how strongly an atom draws electron density toward itself in a covalent bond. Fluorine is the most electronegative element. Oxygen is next. Nitrogen close behind. Metals are generally the least electronegative. When two atoms of different electronegativity form a covalent bond, the electrons aren't shared equally. The more electronegative atom pulls the shared electrons closer. The bond becomes polar. One end carries a partial negative charge, the other a partial positive charge. These partial charges are the source of permanent dipole-dipole interactions. In hydrogen fluoride, the bond is so polarized that the hydrogen atom's nucleus is essentially exposed on one side, which is why hydrogen fluoride forms unusually strong hydrogen bonds. In carbon-hydrogen bonds, the electronegativity difference is tiny, and the bond is essentially nonpolar, which is why hydrocarbons interact almost exclusively through London forces. The practical consequences of electronegativity are enormous. Water's polarity, from the oxygen being more electronegative than the two hydrogens, gives it its extraordinary dissolving power, its high surface tension, its high boiling point. Life uses water as its universal solvent, precisely because water's polarity lets it form strong interactions with charged and polar molecules, while excluding nonpolar ones. The separation of the lipid bilayer from the aqueous interior of a cell, the boundary that defines what is inside and outside, happens because lipid molecules have a polar head that loves water and a nonpolar tail that doesn't, so they spontaneously arrange themselves into a bilayer with all the tails pointing inward, away from water. This self-assembly, driven by electronegativity differences at the molecular level, is how cells have boundaries at all. The gecko story is worth telling in full. Geckos can walk up smooth glass, cling to ceilings, and support their body weight with a single toe. This seemed almost magical until Keller Autumn and colleagues at Lewis and Clark College studied the gecko's foot structure in detail in 2002. Gecko toes are covered in millions of tiny hairs called setae, each of which branches into hundreds of even smaller tips called spatulae. The spatulae are so small, nanometers across at the tips, that when pressed against the surface, they come into very close contact with the surface atoms, close enough for London dispersion forces to act between the spatulae and the surface. Individually, each contact point provides an infinitesimal force, but millions of contact points across the full surface of the gecko's toe add up to enough adhesive force to hold the animal's weight. A gecko's foot doesn't use glue, it uses physics. London dispersion forces, multiplied by geometrically engineered contact area, achieves something that looks miraculous. This inspired a whole field of bio-inspired adhesives. If you could manufacture a surface with similar geometry, millions of tiny, compliant nanoscale tips, you could potentially create a dry adhesive that worked through the same mechanism. Various research groups have made prototype gecko-inspired adhesives from carbon nanotubes, polymer pillars, and other structured surfaces. The challenge is replicating not just the nanoscale structure, but also the self-cleaning property of gecko feet, which seems to come from the geometry sweeping contaminants aside as the foot moves. Now, let's talk about one of the most important things that chemists have figured out how to do, which is look at molecules to determine their structure from first principles without having to build and test every candidate. When you make a new compound in the laboratory, you often start knowing what reaction you ran and what you expected to produce, but you need to confirm that's what you actually got. Or you might start with a substance you've isolated from a natural source and have no prior knowledge of its structure. In either case, you need to work out what the molecule looks like, how the atoms are connected, what bonds are single versus double versus triple, what the three-dimensional arrangement of the atoms is. This is structure elucidation, and for most of the history of chemistry, it was done painfully, slowly, using chemical reactions. You do a series of reactions that specifically broke or formed certain kinds of bonds, and from the results, you deduce what structure could produce those outcomes. It could take years for a complex molecule. Modern spectroscopy changed this completely, and it changed it by exploiting the interaction between matter and electromagnetic radiation in ways that are deeply rooted in quantum mechanics. Start with infrared spectroscopy. Every chemical bond has a natural frequency at which it vibrates. A carbon-hydrogen single bond vibrates at one frequency. A carbon-oxygen double bond vibrates at a different frequency. A nitrogen-hydrogen bond at another. These frequencies fall in the infrared portion of the electromagnetic spectrum. If you shine infrared light on a molecule and scan through different frequencies, the molecule absorbs radiation at the specific frequencies that match its bond vibrations. The resulting spectrum, a plot of absorption versus frequency, is essentially a fingerprint of the functional groups in the molecule. An organic chemist looking at an infrared spectrum can immediately spot whether a compound has a carbonyl group, a distinctive strong absorption near 1700 wave numbers, a hydroxyl group, a broad absorption around 3500, a carbon-hydrogen bond, absorptions in a specific range, and so on. Within minutes, without running any chemical tests, you know what major functional groups are present. Mass spectrometry works completely differently. You vaporize the molecule and bombard it with high-energy electrons, which knock off one electron from each molecule, leaving a positively charged radical ion. That ion gets accelerated by an electric field and then deflected by a magnetic field. Lighter ions bend more, heavier ones less. A detector measures the mass to charge ratio of all the ions produced. The first thing you see is the molecular ion, the intact molecule minus one electron, which tells you the molecular weight of the compound. Then you see fragments, because the molecular ion often breaks apart at weak bonds during the ionization process. The pattern of fragments, which bonds broke, what sizes of pieces were produced, provides information about the connectivity of the atoms. High-resolution mass spectrometry can determine the exact molecular formula of a compound to several decimal places in mass, which dramatically narrows down the structural possibilities. Nuclear magnetic resonance spectroscopy, also known as NMR, is the most powerful of the three, and the one that can, in favorable cases, tell you the complete three-dimensional structure of a molecule. The physics behind it involves placing atomic nuclei, typically hydrogen nuclei, which are just single protons, in a strong magnetic field. Nuclei with non-zero spin can align with or against the magnetic field, and there's a specific frequency of radio waves that will flip a nucleus from one alignment to the other. The crucial insight is that the exact frequency depends on the electronic environment around the nucleus, all the other atoms it's bonded to, what functional groups are nearby, whether there are pi electrons around it. So, a hydrogen atom in a methyl group absorbs radio waves at a slightly different frequency than one in an aldehyde group, which absorbs at a different frequency than one in an aromatic ring, and so on. A nuclear magnetic resonance spectrum tells you, for each distinct hydrogen environment in the molecule, how many hydrogens are in that environment from the intensity of the signal, what the electronic environment around them is, from the precise frequency, and how many neighboring hydrogens they have from the splitting pattern of the signal caused by interactions with neighboring nuclei. Put these pieces together and you can, often without any ambiguity, work exactly how the atoms are connected. Carbon-13 nuclear magnetic resonance spectroscopy gives you information about the carbon skeleton. Two-dimensional nuclear magnetic resonance experiments establish which protons are close to which other protons in space, which can pin down the three-dimensional structure. The MRI scanner in a hospital is actually a nuclear magnetic resonance machine. It uses the same physics, radio waves flipping proton spins in a magnetic field, but applied to the water protons throughout the body, generating images based on the density and relaxation behavior of protons in different tissues. Every time someone has an MRI scan, they're benefiting from quantum mechanical physics, first developed to study the structure of small organic molecules in glass tubes. X-ray crystallography is a technique that determined the structure of DNA, of penicillin, of countless protein targets for drug design. You grow a crystal of the compound, shine X-rays on it, and measure the pattern of diffracted X-rays. The crystal's regular, repeating lattice structure diffracts X-rays in a way that's precisely predictable from the positions of the atoms. And by solving the inverse problem, working backward from the diffraction pattern to the atomic positions, you can determine where every atom in the molecule is in three-dimensional space. The mathematical machinery required to do this is substantial, and for decades it required expert crystallographers doing laborious manual calculations. Now it's mostly automated, and the protein data bank contains over 200,000 solved protein structures, each one determined by X-ray crystallography or related techniques. All of these spectroscopic and structural methods share a common character. They use something fundamental about quantum mechanics: the quantized interaction of matter with electromagnetic radiation to extract information about molecular structure without chemically modifying the molecule. You're reading the molecule's quantum properties with light. There's a concept in chemistry that most people outside the field have never heard of, but that turns out to have life or death consequences and touches almost every drug you've ever taken. It's called chirality, and the best way to introduce it is with your hands. Look at your hands. They are mirror images of each other. Both have 4 fingers and a thumb, arranged the same way, but they're not superimposable. You can't rotate your right hand in 3-dimensional space to make it look exactly like your left hand. They're related by a mirror plane, but not by any rotation. This property, being non-superimposable on your mirror image, is what chemists call chirality, from the Greek word for hand. Molecules can be chiral too, and when they are, the 2 mirror image forms, called enantiomers, are chemically identical in most respects. They have the same melting point, the same boiling point, the same nuclear magnetic resonance spectrum in ordinary solvents, but they interact differently with other chiral molecules. And because the biological world, your enzymes, your receptors, your DNA is built almost entirely of molecules that are themselves chiral, enantiomers can have radically different biological effects. The most horrific demonstration of this was thalidomide. In 1957, a German pharmaceutical company introduced thalidomide to the market as a sedative. It was marketed as safe and mild, a better sleeping pill, particularly recommended for use during pregnancy to treat morning sickness. The company was aware that the molecule was chiral. It had 2 enantiomers, but they made and sold the racemic mixture, which is an equal blend of both. In the following years, approximately 10,000 children were born worldwide with phocomelia, severe malformations of the limbs, with hands and feet attached directly to the torso, having formed without the intermediate long bones. Roughly half of these children died. The survivors carried the visible consequences for the rest of their lives. It was eventually established that one enantiomer of thalidomide, the R form, had the sedative effect that was useful. The other, the S form, was teratogenic. It interfered with the development of blood vessels in the embryo during a critical period of fetal development, which disrupted limb formation. If only the R enantiomer had been used, the tragedy might theoretically have been avoided, except that it turned out thalidomide racemizes in the body. The R form converts spontaneously to the S form and back again in the acidic conditions of the body, so even pure R thalidomide would have produced some S thalidomide in a pregnant woman's body. The consequences of the thalidomide disaster extended across the entire pharmaceutical industry. Drug approval requirements were tightened dramatically in every major country. The FDA, which had already held up thalidomide's approval in the United States through the meticulous skepticism of Francis Kelsey, who demanded more safety data and was later recognized by President Kennedy for preventing the disaster in the US, gained additional power and requirements. Chirality became a central concern in drug development. Companies were now required to either demonstrate that both enantiomers were safe or to develop methods to produce and administer only the active, safer enantiomer. The field of asymmetric synthesis, chemistry that produces one enantiomer preferentially, became enormously important as a result. William Knowles at Monsanto developed the first asymmetric hydrogenation catalyst in the late 1960s, showing that a chiral catalyst, one that is itself non-superimposable on its mirror image, can cause a reaction to produce one enantiomer preferentially. Ryoji Noyori extended this with more powerful chiral metal catalysts. Barry Sharpless developed asymmetric epoxidation, a method for selectively oxidizing one face of a double bond. All three shared the Nobel Prize in Chemistry in 2001 for asymmetric catalysis. The thalidomide disaster also has a strange coda. The drug is back. Thalidomide is now approved for treating multiple myeloma, a blood cancer, and for leprosy complications, and it's being investigated for other cancers and inflammatory conditions. The S enantiomer that causes limb malformations turns out to have anti-angiogenic properties. It prevents the growth of new blood vessels, and this same property that makes it dangerous to fetuses makes it useful against tumors which need new blood vessel growth to expand. A molecule that destroys unborn children has become a tool for fighting cancer, and the darkest episode in the history of pharmaceutical chemistry has produced some of the most important methodological insights in drug development. Chirality shows up everywhere once you look. All naturally occurring amino acids in proteins are left-handed, the L form. All naturally occurring sugars in DNA and RNA are right-handed, the D form. This universal homochirality of biology is itself a deep mystery. In the lab, if you make amino acids from scratch, you always get a racemic mixture unless you use chiral starting materials or chiral catalysts. But life uses only one hand. The leading explanation is that there was a tiny random excess of one enantiomer in the earliest chemistry, perhaps due to polarized light from a neutron star irradiating the early solar system's chemistry. And that tiny excess got amplified by autocatalytic processes into the complete dominance of one-handedness we see today. This is connected to the origin of life problem and remains an area of active research. Your nose experiences chirality directly, though you probably never knew it. Carvone, the molecule responsible for the smell of caraway seeds and spearmint, exists in two enantiomers. The R form smells like spearmint. The S form smells like caraway. Same molecular formula, same atoms, same connectivity, just a different arrangement in three-dimensional space. And your nose's chiral receptor proteins distinguish them effortlessly. The molecules fit differently into the receptor's binding site, the way a right-handed glove fits differently on a right hand versus a left hand. Let's go somewhere that sits at the fascinating boundary between chemistry and architecture, supramolecular chemistry. All the chemistry we've talked about so far involves covalent bonds, atoms sharing electrons to form molecules. Supramolecular chemistry asks, what structures can you build using only the weaker interactions? Hydrogen bonds, electrostatic attractions, van der Waals forces, hydrophobic effects, all of the intermolecular forces we discussed. If you design molecules whose shapes and charge distributions make them prefer to stick together in specific geometries, can you build complex structures without making a single covalent bond? The answer is yes, and the structures you can build are remarkable. The foundational concept is molecular recognition. Molecules that fit together specifically like a key and a lock, held together not by covalent bonds, but by the complementary arrangement of weaker interactions. Charles Pedersen discovered crown ethers in 1967, ring-shaped molecules with oxygen atoms arranged to perfectly complement the size and charge of specific metal ions. A crown ether of exactly the right size grabs its preferred metal ion from solution with surprising strength, even though each individual oxygen-metal interaction is weak. Donald Crum and Jean-Marie Lane extended this into three-dimensional cage-like molecules, cryptans, that completely enclose metal ions, and into broader principles of designing host molecules to selectively recognize specific guest molecules. All three shared the Nobel Prize in 1987 for the conceptual framework of supramolecular chemistry. The biological world had been doing supramolecular chemistry all along, of course. The double helix of DNA is held together by hydrogen bonds between complementary base pairs, not covalent bonds between the two strands. The structure of a protein involves the backbone's hydrogen bonds but also an enormous number of weaker interactions between side chains. The binding of a drug to its target is typically supramolecular, hydrogen bonds, hydrophobic contacts, van der Waals interactions, which is why drugs can be washed out of a receptor under the right conditions. Unlike covalent drugs that chemically react with their target, self-assembly is what you get when molecules are designed so that their supramolecular interactions drive them to arrange spontaneously into a specific structure. Soap micelles are simple version. Soap molecules with a polar head and a non-polar tail spontaneously arrange into spheres, with all the tails pointing inward, away from water, and all the heads facing outward into the water. The structure assembles without any input of energy or information from outside. The shape is encoded in the molecular geometry. More complex self-assembled structures include vesicles, which are hollow spheres with a bilayer wall, the structural basis of cell membranes, and the lipid nanoparticles used to deliver messenger RNA vaccines. Two-dimensional self-assembly on surfaces has produced atomically precise structures of extraordinary complexity. You can design organic molecules with specific shapes and interaction profiles that, when deposited on a metal surface under the right conditions, tile into precise patterns that repeat perfectly across a surface area containing billions of molecules. The pattern is encoded in the molecular structure. No external template is needed. The system finds its own order through the thermodynamics of supramolecular interactions. Metal-organic frameworks, sometimes called MOFs, are perhaps the most dramatic products of supramolecular chemistry thinking applied to materials design. They're crystalline materials made by coordinating metal ions or metal clusters with organic linker molecules, producing open, porous, three-dimensional framework structures with enormous internal surface areas. The record metal organic framework has an internal surface area per gram of material of over 7,000 square meters, 1 gram with the surface area of more than a football field. These materials can selectively absorb specific gas molecules based on the size and chemical environment of their pores, which makes them candidates for carbon capture, gas storage, gas separation, and drug delivery. The pore geometry and chemistry can be tuned by choosing different metal nodes and different organic linkers, modular materials design at the molecular level. The vision that animates the most ambitious work in supramolecular chemistry is molecular machines. If you can design molecules that change shape or orientation in response to a chemical signal, a light signal, or a pH change, and if you can connect those shape changes to mechanical work, you have the beginnings of a molecular machine. Fraser Stoddart at Northwestern University has made rotaxanes, molecules where a ring molecule is threaded onto a dumbbell-shaped axle and can slide back and forth along the axle in response to chemical signals. Fraser Stoddart, Ben Feringa, and Jean-Pierre Sauvage shared the Nobel Prize in 2016 for the development of molecular machines. Feringa's group made the first molecular motor, a molecule that rotates unidirectionally around a double bond when irradiated with light in 1999. The rotations are measured in individual molecular events detected by spectroscopy, but the principle is the same as a macroscopic motor, converting energy into directed rotational motion. The long-term vision for molecular machines goes in multiple directions. Medical nanorobots, molecular machines that could navigate through the bloodstream, detect cancer cells, and release drugs specifically at the tumor site are a concept that has been in science fiction for decades. The chemistry that would be needed to build them is becoming real, piece by piece. DNA origami, using the precise geometry of base pairing to fold DNA strands into specific 2- and 3-dimensional structures, can produce nanoscale shapes with sub-nanometer precision and can be programmed to open and close in response to specific molecular signals. DNA origami has already been used to make nanoscale cages that open in the presence of cancer biomarkers, releasing their drug payload at the target. There are some deep theoretical puzzles in chemistry that never quite get resolved, that sit at the boundary between what we know and what we might eventually figure out. Let me go through a few of them, because they reveal something about the limits of our current understanding and the directions the field might move in. One of them is the question of chemical intuition itself. Experienced chemists develop a sense for which reactions will work and which won't, which molecular scaffolds will be stable and which won't, which synthesis routes have the right character for a given target. This intuition isn't fully articulable as rules. It's a kind of pattern recognition trained over years of experimental experience, reading the literature and building mental models of how molecules behave. When a veteran organic chemist looks at a proposed synthesis route and says, "That step seems risky," or "This intermediate will probably isomerize," they're often right, but they can rarely fully explain why at the level of first principles. This raises an interesting philosophical question about chemistry as a science. There's a formal, algorithmic layer, thermodynamics, kinetics, quantum mechanics, and then there's a tacit, experienced, intuitive layer that can't be fully reduced to the formal layer. The gap between the two is where most of the practical skill lives. AI is now being trained to acquire this tacit knowledge from the corpus of published chemistry, millions of reactions, outcomes, and conditions. And it's doing surprisingly well at reproducing the pattern recognition. But whether AI chemical intuition and human chemical intuition are the same thing, or whether they're complementary, is an open question. Another puzzle. Why are some chemical reactions so much harder to reverse than theory would suggest? Thermodynamics tells you the free energy difference between starting materials and products, and kinetics tells you the rate. But in practice, reactions often have strong kinetic traps. They get stuck in intermediates that aren't the thermodynamic product, and they stay there for reasons that aren't always easy to predict. The landscape of chemical space, with its valleys and ridges and saddle points of energy, is navigated by molecules stochastically at room temperature, and the routes they take, which products they find, which intermediates they pass through, are sensitive to small details of conditions in ways that are hard to capture in simple models. The folding of proteins is this problem made even more complex. The thermodynamically stable folded state of a protein is reached in milliseconds, despite the fact that the number of possible conformations is astronomically large. Leventhal's paradox, named for the protein chemist who pointed it out in 1969, asks how proteins can fold so fast if they're searching randomly through conformation space. The answer is that the search isn't random. There are thermodynamic biases that funnel the folding toward the native state through a funnel-shaped energy landscape, without requiring the protein to visit all possible conformations. But the exact nature of those funnels and why some sequences fold reliably while others misfold and aggregate is still an area of active research. Misfolded proteins are the cause of amyloid diseases, Alzheimer's, Parkinson's, type 2 diabetes, all of which involve specific proteins aggregating into structured deposits that kill neurons or damage tissues. Then there's the question of the chemical basis of consciousness. I'm not suggesting consciousness is a solved problem or that chemistry alone explains it, but the basic fact of subjective experience, the fact that there is something it is like to be you, looking at a screen, processing these words, is implemented in chemistry. Neurons fire through electrochemical signals. Neurotransmitters cross synapses through diffusion. Receptors bind those neurotransmitters and change the electrical state of the receiving cell. The entire computation of a brain is, at its base level, a biochemical process. Understanding exactly how this chemistry gives rise to experience is the hard problem of consciousness, and it's almost certainly not going to be solved at the level of chemistry alone. But it's worth acknowledging that chemistry is the substrate. Anesthetics are one of the more mysterious things in pharmacology precisely because of this. General anesthetics cause reversible loss of consciousness. They work. They've been used in surgery for over 150 years. But exactly how they work at the molecular level remains contested. The leading hypothesis involves their effects on ion channels in neural membranes, specifically their ability to perturb the lipid bilayer and change the behavior of membrane proteins. But the precise mechanisms and why such chemically diverse molecules, inhalational gases like sevoflurane, intravenous drugs like propofol, even noble gases like xenon, all produce the same behavioral endpoint while interacting with different molecular targets is still not fully understood. The phenomenon we use to perform virtually all major surgery is, at its chemical basis, mysterious. Let's also spend some time on the chemistry that might matter most for the immediate future of human civilization, the chemistry of climate and energy. Carbon dioxide is a simple molecule, one carbon, two oxygens, a linear structure with two carbon-oxygen double bonds. Its chemistry is not complicated, but its physical chemistry is. Carbon dioxide is essentially transparent to visible light. Sunlight passes through it without interaction, but it absorbs strongly in the infrared. When solar radiation hits the Earth's surface, it's absorbed and re-emitted as infrared radiation. Carbon dioxide and other greenhouse gases intercept that infrared radiation and re-emit it in all directions, including back toward Earth's surface. This is the greenhouse effect, and it's not a controversy. It's a direct consequence of the spectroscopic properties of the carbon dioxide molecule, which can be measured precisely in a laboratory. More carbon dioxide in the atmosphere means more infrared absorption, which means more warming. The chemistry of decarbonizing the global economy is therefore urgent in a way that no other application of chemistry currently is. One front is better solar cells. Silicon photovoltaics currently dominate the market, converting sunlight to electricity at efficiencies around 20 to 25% for commercial panels. Perovskite solar cells, named for the crystal structure they share with the mineral perovskite, have gone from laboratory curiosities to efficiencies matching or exceeding silicon in about 15 years. One of the fastest improvement trajectories of any new technology. They can be processed from solution, making them potentially much cheaper to manufacture. The remaining challenges are stability. Perovskites currently degrade in moisture and under extended ultraviolet exposure, and the toxicity of the lead-containing versions that perform best. The chemistry of stabilizing perovskites while maintaining performance is one of the most active research areas in materials chemistry right now. Hydrogen as a fuel is another front. Hydrogen contains more energy per kilogram than any other chemical fuel, and burning or electrochemically converting it produces only water. The problem is making it cleanly. Currently, most hydrogen is made by steam reforming of natural gas, which releases carbon dioxide. Electrolysis of water, splitting water into hydrogen and oxygen using electricity, produces clean hydrogen if the electricity is from renewable sources, but requires better catalysts to reduce energy consumption. The ideal would be a catalyst for the oxygen evolution reaction, the half reaction where water is oxidized to produce oxygen. That's as efficient as platinum, but made from earth-abundant materials instead. Biology solves this with the oxygen evolving complex of photosystem 2, a manganese-calcium cluster that splits water with extraordinary efficiency and uses no precious metals. Chemists are trying to replicate this, using knowledge of the biological mechanism to guide the design of synthetic catalysts. It's slow, hard work, but the prize, cheap, clean hydrogen, is enormous. Direct air capture of carbon dioxide, pulling carbon dioxide directly from the atmosphere using chemical sorbents is the other end of the problem. Not reducing emissions, but actively removing the excess carbon dioxide already accumulated. Current direct air capture plants use strong alkali solutions or amine functionalized solid sorbents that react with carbon dioxide, then release it at high temperature for storage or use. The energy cost is high, which is why it's expensive. The chemistry of better sorbents, ones that bind carbon dioxide strongly enough to capture it from 400 parts per million in air, but release it at lower temperatures, could dramatically reduce the energy cost. Metal organic frameworks with carbon dioxide selective pores are being studied. Enzymes based on carbonic anhydrase, the enzyme that speeds up carbon dioxide hydration in your blood, are being considered. The whole field is racing against the accumulation of carbon dioxide in the atmosphere and the consequences of that accumulation. Battery chemistry deserves its own extended treatment because it's the linchpin of the transition to electric vehicles and grid energy storage. The lithium-ion battery that currently dominates is genuinely impressive, but it has well-known limitations. The energy density is limited by the amount of lithium that can be intercalated into the electrode materials. Safety concerns arise from the flammable organic electrolytes and the possibility of thermal runaway, a cascade of exothermic reactions that can cause a battery to catch fire. The supply chains for cobalt used in many cathode materials are concentrated in politically unstable regions and involve documented human rights abuses. Solid-state batteries, which replace the liquid organic electrolyte with a solid ceramic or polymer electrolyte, would eliminate the flammability risk and potentially allow the use of lithium metal anodes, which can store more energy than graphite. The challenge is that solid-solid interfaces between electrode and electrolyte don't conduct ions as easily as solid-liquid interfaces, and the volume changes in the electrodes during charge and discharge crack the solid electrolyte. These are solvable chemistry problems, and several companies are claiming to be close to solving them. Lithium-sulfur batteries offer even higher theoretical energy density than lithium-ion because sulfur can accept 2 electrons per atom during reduction compared to 1 for most current cathode materials. The challenge there is the formation of soluble polysulfide intermediates during discharge that migrate through the electrolyte, reducing efficiency. Sodium-ion batteries use sodium instead of lithium. Sodium is vastly more abundant, and while they have lower energy density, they may be adequate for stationary grid storage where weight is less critical. The chemistry of each of these battery systems is specific and intricate, involving the details of electrode-electrolyte interfaces, the transport of ions through solid or liquid media, the thermodynamics of intercalation reactions, and the kinetics of side reactions that cause capacity fade over time. Getting them right requires the entire toolkit of modern chemistry: computational modeling of interfaces, in situ spectroscopy to watch what happens inside a working battery in real time, synthesis of new electrode and electrolyte materials, rigorous electrochemical characterization, and there is no chemistry problem whose solution would do more immediate good for the energy transition. There's one more thing worth covering before we look at where all of this is going, and it's chemistry's most uncomfortable relationship with its own most powerful tools. The same understanding of molecular structure and reactivity that produces medicines produces poisons. The same synthetic methods that make drugs make weapons. The same knowledge of catalysis that enables clean industrial chemistry has enabled chemical weapons. This isn't a peripheral concern in the history of chemistry. It's woven through it from the beginning. Fritz Haber, who won the Nobel Prize in 1918 for the nitrogen fixation process that feeds billions, personally supervised the first deployment of chlorine gas as a weapon at Ypres in 1915, killing thousands of soldiers. He considered chemical weapons a legitimate and even humane alternative to conventional warfare. His wife Clara, herself a chemist and a pacifist, disagreed profoundly, so profoundly that she shot herself during the night of the victory celebration he threw at their Berlin home. Roughly 9 days after the Ypres attack, he left for the Eastern Front the next morning. The development of nerve agents in the 1930s and 40s was a direct consequence of the organophosphate chemistry that was also producing insecticides. German chemist Gerhard Schrader, working on developing insecticides for IG Farben, synthesized tabun in 1936 and recognized that it was extraordinarily toxic to humans. Tabun, sarin, and soman, the first generation of nerve agents, work by irreversibly inhibiting acetylcholinesterase, the enzyme that breaks down the neurotransmitter acetylcholine after each nerve impulse. Without the enzyme working, every motor neuron fires continuously and uncontrollably. Muscles cramp and convulse. Breathing stops. Death occurs in minutes. The mechanism is the same as how organophosphate insecticides kill insects. The difference is dosage and selectivity. The Chemical Weapons Convention, which entered into force in 1997, prohibits the development, production, stockpiling, and use of chemical weapons. Most countries have signed it and destroyed their declared stockpiles. But the use of sarin in the Syrian civil war and the poisoning of Sergei Skripal in the United Kingdom using a fourth-generation nerve agent called Novichok demonstrate that this knowledge hasn't disappeared. It can't disappear. It's in the scientific literature and in the minds of people trained in chemistry. The same understanding of enzyme inhibition that enables drug design can be turned toward developing agents that inhibit enzymes you need to stay alive. This dual-use problem is intrinsic to chemistry in a way that doesn't have a clean solution. The knowledge that enables the most beneficial applications also enables misuse. The response has been international treaties, export controls on precursor chemicals, oversight of research with potential weapons applications, and the professional norms of chemists themselves, most of whom choose careers specifically because they want to help, not harm. But the tension is real. and any honest account of chemistry has to acknowledge it. There's a broader thing to say here at the end of all of this about what chemistry actually is. It's tempting to summarize chemistry as the study of matter and its transformations, which is technically correct and completely insufficient. Chemistry is the level of reality at which the universe becomes materials, where quantum probability distributions become atoms, and atoms become the periodic table, and the periodic table becomes molecules, and molecules become enzymes and drugs and DNA and steel and diamond and chocolate and poison and everything you can touch. Every field of science has a level at which its explanations live. Physics explains forces and fields and the behavior of particles. Biology explains organisms, ecosystems, evolution, cellular function. Chemistry explains the level in between, the molecular architecture that makes biological systems possible, the material properties that make physical objects real and tangible, the reactions and transformations that connect the inorganic world to the living one. The alchemists who started this story, working in crude furnaces with unclear theories, chasing dreams of gold and immortality, were doing something genuinely important even when they failed. They were insisting that the material world was intelligible, that its behavior could be understood and predicted and controlled. They were right. It just took a while to figure out how. Lavoisier weighed everything and showed that mass was conserved. Dalton proposed atoms and calculated their relative masses from chemical ratios. Mendeleev arranged the elements and predicted the ones that were missing. Thomson and Rutherford and Bohr dismantled the simple atom and found structure inside it. Schrödinger and Heisenberg built the mathematics of quantum mechanics that explained that structure from deeper principles. Watson and Crick and Franklin, and it should be all three names, solved the structure of DNA and connected chemistry to heredity and evolution. The people who built Haber-Bosch fed the world. The people who built penicillin saved hundreds of millions of lives. The people who understood nuclear fission changed the history of the 20th century in ways we're still living in the shadow of. And the people working right now on quantum computers in clean rooms, on protein structures in cryo-electron microscopes, on molecular dynamics trajectories in data centers, on new battery materials in electrochemistry labs, are doing the same thing, trying to understand the material world more precisely, trying to control it more reliably, trying to build things that haven't existed before. Chemistry isn't done. It's not close to done. Every atom in your body has been through the interior of a star. Every bond holding your cells together is electrons shared between nuclei, obeying quantum rules written into the structure of the universe at the deepest level we can currently access. Every breath you take is an oxidation reaction, a combustion so gentle and controlled that it sustains rather than destroys. Every thought you have is electrochemistry, ions moving across membranes in patterns that somehow add up to experience. The diamond that Lavoisier burned in 1772 left behind a gas and a question: what is fire? The answer, when it finally came, was not a simple one. Combustion is a chemical reaction, which means atoms rearranging themselves to lower their total energy, releasing the difference as heat and light. Fire is matter trying to reach a more stable state. And so, in a way, is everything else that's chemistry.